the publications of the university is nearly 400, of which mechanical it contributes nearly 50 publications in the last 4 years in the reputed international journals. And then I'm happy to say that another 45 more publications are in review. Apart from this, the sponsored research also, apart from academic research, the sponsored research also has got a major role to play in our school. So as of today, I'm proud to say that the School of Mechanical Engineering, we are having nearly 55 lakh worth of projects from centrally funded organizations like DST. Then we have got projects from SERB, and we also got the first industry-sponsored project of VITP University from Dassault Systems. And then apart from this, projects nearly worth 2 crore are under review with the different governing funding agencies of the Government of India and also private industries. The IPR, the intellectual property rights, which are an outcome of the UG students' work, PG students' work, faculty who support the students and co-work with them, has also taken a key role. Now, as of today, the School of Mechanical Engineering has got 1 patent granted patent to its credit. And apart from that, we have got nine more patents which are published by the School of Mechanical Engineering in a very short span of 4 years. Now, apart from this, the school is very actively participating in the conducting various workshops, and we also organize conferences. We have conducted several workshops in the past, and probably in 2021, because of the pandemic scenario and all, this is the first workshop we are organizing in the year 2021. And coming to international conferences, right in the 3rd year after its starting in the year 2020, we have conducted an international conference which has got a huge response from across the globe, the International Conference on Applications of Fluid Dynamics. And in the year 21-22, we have planned 2 international conferences. One in the month of December 3rd to 5th, 2021. There is a prestigious ISTAM conference, Indian Society for Theoretical and Applied Mechanics. And apart from this, in January 2022, from January 22nd to January 24th, 3-day international conference on advances in mechanical engineering and material sciences. Even for this conference, with the prestigious VIT brand, we have attracted nearly 300 abstracts till date. The abstracts are still open till 30th of this month, so the interested people also can submit. And apart from this, in 2022, we are also planning 1 more national conference. So the School of Mechanical Engineering has made its presence in terms of the publications, in terms of research, in terms of contributing to technical support to the UG students, PhD scholars, sponsored research. So you name it, the Mechanical Engineering School has contributed its might. So in addition to support all these things, the fundamental thing which is required is the research infrastructure and research facilities. The management, particularly our Vice Chancellor, he has been very kind enough with a visionary spirit of promoting research. Till date, like we have, the School of Mechanical Engineering has got 250 lakh worth of research equipment. To name a few, like we have got the dynamic mechanical analyzer, and then we have got the rheometer, the scratch tester, many equipment we have got. We support industry in testing in the form of consultancy. We also accept consultancy from other academic institutes to help them do research. So the facilities are open for in terms of consultancy. So I hope with all these facilities and the support from the higher management, the VC sir, Registrar sir, and the support from our school team, I hope the School of Mechanical Engineering will organize many such events and go forward, taking the support of the various other schools. And I wish that in today's workshop, the focus on manufacturing techniques will be in detail dealt by the various experts who are present here. And we have got Sri Jayasingha Reddy Garu, who is a pioneer, an entrepreneur who has been working. I hope his inputs also will throw light on us how the industry, manufacturing sector is moving towards. So with this, I welcome all the participants, faculty members, so that you will be fully benefited with the technical expertise of various experts present, drawn from different institutes, with nearly 150 participants across 15 different states of the country. I hope and I wish the coordinator, Dr. Pankaj, a big success. I welcome you all once again. Thank you. Thank you for this opportunity.
Thank you, sir. Next, we have Dr. Pankaj Tambe, professor and the coordinator of the workshop, professor at Mechanical Engineering School at BITAP University. I would like to call upon him to give a brief overview of the workshop.
Thank you, Rakhi ma'am. As a coordinator, I welcome everyone, and especially respected chief guest Jaisima Reddy sir, Vice Chancellor sir, Registrar sir, Dean sir, all the participants, faculty colleagues, and our own research scholar. I welcome everyone. So we know that material plays a very important role in our life, and the processing of material add value in the form of components and the product. And additive manufacturing create an opportunity for the industry to add more value to the existing product. So in this regard, with the leadership from Vice Chancellor sir, with his guidance, we are organizing this 3-day workshop on additive manufacturing. And in this workshops, the various resource persons from Indian Institute of Science, Bangalore, IITs, NITs, and our own institute, VITAP, and VIT Vellore campus, a few resource persons are there. And these faculty members are working in the area of additive manufacturing and advanced material processing. I hope the workshop is a platform to learn the insight about an additive manufacturing for those who are joining, and the insight about the processing and the characterization is the very important aspect. So current researchers are looking at. And in addition, advanced material has to be processed with the help of additive manufacturing. So with this brief idea about this workshop, there are several sessions. Each day there are 3 sessions we have planned on the metal-based additive manufacturing and polymer-based manufacturing. On the last day, it concentrates on advanced material processing, where the additive manufacturing technologies need to be used, and it will help the industry to manufacture the product as per their need. So with this brief about the workshop, I just conclude. Thank you.
Thank you, sir. Next, I would like to call upon our Honorable Vice Chancellor, sir, Dr. S.V. Kota Reddy, to speak to the gathering.
Very good morning to everyone. Happy Guru Purnima to everyone. On this occasion, we are organizing this workshop. It is really very good coincidence. Managing Director, MD Industries, Sri C.H. Jaisima Reddy Garu, Sir VITAP University, Dr. C.L.B. Shivakumar Sir, Dean School of Mechanical Engineering, Dr. Rama Shrikant, coordinator for this workshop, Dr. Pankaj Tambe, distinguished speakers, distinguished guests, delegates attending this workshop, faculty and staff members, research scholars, and my dear students. It is with great pleasure that I welcome you all to this 3-day national workshop on advances in material processing, 3D printing, and opportunities. My hearty congratulations to the School of Mechanical Engineering to organize this national level workshop.
Thank you, sir.
This kind of workshop, domain specific workshops, are very much useful for the enhancement of expertise in a specific technical area. And the smart materials and 3D printing are the latest areas, emerging areas. And I appreciate the school to take this topic for the workshop. It's really a very good topic. And this kind of workshops also provide the platform for experts from industry and academia to share their knowledge and experience in the specific areas like advanced materials and 3D printing. If you see the innovations in the entire world, in one way or the other, all the major scientific inventions have been dependent on the materials available at that time. For example, Thomas Edison invented the electric bulb. We all know that. Because at that time, the material he was searching for, which can withstand high temperature, and that time he found that tungsten was the material, and he could invent that and use that material. And similarly, when Wright brothers invented their airplane, okay, then that time they were also looking for the light materials, and they could find aluminum, and their engine was made of aluminum, not with the steel, because the weight has to be as low as possible, and it has to withstand the it has to have enough strength also. Therefore, materials play an important part in defining the function of the structure. They are used for making any kind of innovations or any kind of product. In the 21st century, we all know that the entire world is moving towards automation and artificial intelligence. So it becomes necessary that the structures that are made be intelligent and smart, so as to adopt their surroundings, thus increasing efficiency and reducing the complexity in designing. There is a need to develop smart structures for aerospace applications, which can suffice the demand on the expanding industry. The smart materials like shape memory alloys, SMA, then piezoelectric materials, then carbon fiber reinforced polymers, then shape memory polymers, and so on. There are so many new materials are coming up. And as I mentioned earlier, it's an emerging area, and new materials have to be invented, many, for rapid change in the technology and rapid change in the innovations to meet. Then 3D printing is very emerging area, very interesting area, and numerous industrial applications like rapid prototyping, rapid manufacturing, 3D printing, implant and medical devices, and so on. And everywhere it is being used. Now, in fact, with using 3D printing, a small item also can be manufactured, and a building also can be constructed. Okay, then, for example, the world's largest building, 3D printed building, is in Dubai. And actually, the area of that is around 650 square meters, and the height is 9.5 meters, and it is two-storied building. And also, it entered into the Guinness Book of World Records. Now, therefore, the applications, if you see 3D printing, it is actually widely spread across the industry. And of course, even in the university also, if we have 3D printing, we can produce our own, we can produce small components in the university itself to use in various applications. For example, in robotics lab, if you have 3D printer, we can manufacture small items required for to construct the robots. Therefore, 3D printing is very emerging area. And of course, VIT AP University is going to establish one center of excellence in 3D printing, that is additive manufacturing. We are in the process of establishing center of excellence in that area. And at VIT AP University, what are the various focus areas? I just wanted to explain. I just wanted to speak on a little on those things. Now, Dr. Amashikant already explained how the mechanical engineering school is working on all those areas. But I will talk about the research and innovation, what is happening at the university level. Okay, now, one of the important area is research, as I mentioned earlier. In the research, we are actually trying to increase the quantity and quality of the publications. I'm very delighted to inform you that our faculty members have published more than 400 papers in Scopus Index journals with the H index of 18. This is a very good achievement. As a new university, it is a really big achievement. But however, we're actually striving for more number of quality publications in Scopus Index journals. Our aim is to publish 3,000 papers by 2025. It is actually now we are at 400. we have to increase it to 3,000 by 2025. So, I mean, I'm confident that with the dedicated efforts of our faculty members and the research scholars and students, we'll be able to achieve this number. And another area is that we are organizing the international conferences at VIT AP University. This year, we are planning to organize 9 international conferences. Definitely, these international conferences will provide platform for the researchers to share their findings. I mean, we invite the keynote speakers from various international universities also. Okay, then we are actually another area where we are focusing is recruitment of the research scholars. As of now, we have 268 research scholars, and this month, I mean in August month, we are going to add 200 more research scholars, and we pay them 20 to 25,000 per month as a stipend to all these research scholars. As I mentioned earlier, we are also focusing on establishment of the centers of excellence and with the state-of-the-art equipment for advanced research. And one of them is additive manufacturing. The other centers are like AI and robotics, IoT, cybersecurity, image and signal processing, renewable energy, etc. And we are looking forward for the collaboration from the industries. Already, actually, we collaborated we are going to collaborate with the Intel for IoT, the Center of Excellence. And we are actually discussing with some of the international universities also to have the collaboration in these centers. And other area of our focus is innovation and incubation. Projects of societal relevance, campus-specific and industry-specific are also supported through Innovation and Incubation Center. In the current year, we are actually a total of 51 projects are supported with a total grant of 43 lakhs. This is complete to the internal funding. This funding will be used towards social, campus-specific projects. We have submitted project proposals worth of 5.5 crores to various government and private funding agencies. I am confident that some of these fundings will get through. The university has a dedicated space of 10,000 square feet for the technology incubation center. And other very important area is filing IPR. Okay, then as of now, our faculty members published 58 patents. Okay, then we are aiming to file more than 160 patents in 1 year through our Innovation and Incubation Center. And again, if we publish 160 patents in one single year, it would be a biggest achievement, and probably we will become #1 in the country, first university in the country to publish those many patents. I am looking forward to achieve this great goal. Okay, then before, actually I have so many things to talk, but due to lack of time, I'll conclude my speech. And before I conclude, I would like to appreciate the efforts of Dr. Rama Srikanth, Dean School of Mechanical Engineering. In a very short span, actually he is organizing this national level workshop. And of course, I should appreciate the efforts of Dr. Pankaj Tambe and for his tireless efforts as coordinator, and Dr. Ambush Sharma, the co-coordinator of this workshop. And also I appreciate the efforts of other faculty members and students to organize this workshop successfully. I wish you all the very best. Thank you very much.
Thank you so much for your encouraging words, sir. Our chief guest for today's event is Sri Jayasimha Reddy Garu. He is the Managing Director of MTE Industries, Hyderabad. He has obtained his master's degree in Design of Mechanical Systems at the George Washington University, USA. He has been heading MTE as a major name in machine tool building in India. Sri Jayasimha has led the company with a focus on innovative technology with global standards in terms of quality and reliability. Under his leadership, MTE has marked its presence on the global platform and has clients across 5 continents. Its collaboration with Escoffier SAS France and SMOC France marks the presence of MTE in the world map. And Sri Jayasimha has played a key role in materializing this collaboration. Under his able leadership, The company was successful in implementing ISO 9001-2008 standards in terms of stringent quality and reliability. MT has expanded by leaps and bounds under his able managerial skills and is a major supplier of automotive components to auto majors like Tata, Hero, Mahindra, Nissan, just to name a few. Above all, Sri Jayasimha Garu is a visionary and a major philanthropist in the state of Telangana. He's strongly carrying forward the agenda of Beti Padhao and Beti Bachao by helping poor girls in materializing their higher education, I'm told. We are glad to have you here, sir. As a successful entrepreneur and a committed philanthropist, we would like to welcome you to this event. I would like to call upon you to deliver your inaugural address to the gathering now.
Thank you, madam.
Thank you, sir.
Good morning, everyone. I'm very happy and thankful to the whole VIT team for organizing a national level workshop and calling me as a chief guest. I'm very honored. So as Ms. Raki already briefed about me, so MT Industries is basically into three different verticals. One is the machine manufacturing business, and second one is the tool manufacturing business, and the last one is the automotive part manufacturing business. And we have manufacturing facilities in Hyderabad and Pune. So in total, there are around 350 people working in the whole organization. And we are a turnover of around 150 crores ended last year. So this is a brief about the organization which I am leading right now. And I want to share a few of my experiences with respect to 3D printing and the latest manufacturing technologies which the industry is seeing today. So to start with, I'm very thankful to Dr. Kota Reddy Garu, Dr. Rama Srikant Garu for chasing me, honestly, because it was a very short notice for me. So, but still, Mr. Rama Srikant, the way he pursued, I appreciate that. I'm very thankful to him.
Thank you, sir.
So coming to the subject, I have a fairly good idea about the 3D printing technologies. So I want to share a few of my experiences with the team here and the participants. So the 3D printing technology started in the early 80s with the idea of rapid prototyping. So that means that, it the technology, when it started, it was more into sort of creating something which was very difficult in those days by using conventional methods of manufacturing. So it was the whole idea of creating a shape by using some very, very low quality materials like plastics and all. So since then it started and it evolved and it had taken to a greater heights, and the way it evolved is it started with rapid prototyping. And then when it comes to automotive segment, I want to share a few experiences which we had with auto giants like Tata Motors, Mahindra and Mahindra. We constantly work with them on various R&D projects. And then I see the amount of money they have spent in the past. It's more than, there are few projects in which they have spent more than 10 crores to 15 crores of rupees just to create a few net shapes, which were very difficult to create, using conventional methods. So we worked with them very closely in creating many parts, and the amount of efforts, money they have put in to create the shapes and, ultimately bring out the vehicle. So it was very difficult and very expensive in those days. And we have produced some parts for Tata Motors wherein the contracts were amounting to more than 5 crores, which they have paid to us. So starting from then, today, the amount of money and efforts they are investing in using 3D printing technology is very nominal. And the efforts, the time which they invest are very less compared to what they have done 10 to 15 years before. So, and it's not only with the auto segment, 3D printing technology is evolving and spread across almost all the industries in the world. When it goes to aviation industry, I have learned a very interesting thing. very recently, that there were in Boeing 787 Dreamliner aircraft, there was a assembly where 20 individual parts were welded together to create a net shape. And after they introduced the 3D printing technology, they have reduced the weight to 25% lesser than what they have done before. And then it is 5 times stronger than what it was before. So this shows a small example of what 3D printing technology can do and can evolve into in the coming future. And when it goes to the construction industry, as Dr. Kota Reddy Garu rightly said, there are methods to create a brick, and also there are methods to create a whole house. So we can imagine the amount of potential and then the amount of technology involved in the 3D printing. So it again goes to the health industry, where there are implants like hip joints, knee joints, which are very critical to create, and it takes a lot of time and money to create those shapes. But it is done very economically and very quick using a 3D printing machine. So I have bought few machines where we have a grinding machine from Germany that can create a hip joint or a knee joint from a solid block, and we have spent more than 5 crores rupees for that machine. And 3D printing machine would not be that expensive. I'm very sure about that. So that shows how the 3D printing technology is evolving, and then it is taking over all the critical and very complicated processes and making the lives easier. So as I said, it started with a very raw idea of creating something which was very critical, very impossible in the 80s. So now it has evolved to a very cost-effective solution and used across all the industries. And then I have fairly learned about the activities what VIT is doing right now, and I appreciate the whole team for taking the initiative of creating activities like this, and then the research projects what you are doing. And MT Industries would be very happy to get associated with the VIT. So I would like to hear from Mr. Kota Reddy Garu maybe very soon in the future that we would be very happy to associate with VIT. So with having said all these things, I want to share few of the perspectives for the participants and the patrons in this attending the workshop. So I want to suggest and then motivate the participants in this workshop to take full advantage of this workshop, and the dignitaries who are participating, who are about to train them, coach them, to take full advantage of this workshop and make the full use of it in achieving their goals in their career. So with that, I want to conclude by saying few lines about the industry, what it is going right now, and the problems what we are facing right now are mainly with respect to the skilled manpower, where automation and latest manufacturing techniques, adapting those techniques is the only way out for the industry to survive in the future. So I want to encourage, I want to suggest, advise the participants to think in that direction and then adapt themselves to all these latest techniques and make their careers prospective. Thank you.
Thank you. Thank you, sir.
Thank you, sir. Thank you for that informative speech and addressing our gathering. To conclude the inaugural ceremony for today, I would like to welcome Dr. CLV Shivakumar, sir, Registrar, Honorable Registrar of VIT AP University, to deliver the vote of thanks.
Thank you, madam. Good morning. I join our esteemed Vice Chancellor, sir, inviting you all to this workshop with a respectful wishes to all the teachers attending this workshop on this Guru Purnima day. And just now I saw a message from one of my friends saying that whoever is playing the role as a teacher in their own respective field to all of them respectful tributes, as including our today's chief guest, Jayasima Reddy sir. The reason to say this, today's chief guest, dear participants, please understand that before saying few words about this workshop, I really appreciate the School of Mechanical Engineering initiating this kind of very landmark activities, as our Dean and Jayasima Reddy sir pointed out very clearly. This is an important and landmark occasion. 15 states are participating today's workshop, for 3 days workshop. About the state universities, technical universities, IITs, NITs are participating. I'm very glad that the efforts of the faculty coordinator arranging this very timely workshop, a skillful workshop, Dr. Tambe, his efforts are very successful, and I'm sure under the guidance of the Dean, School of Mechanical Engineering, in the days to come, we will be having many more activities. Even the participants would be from international institutions very soon. All these are happening in our institution, following the keen vision of our beloved esteemed Vice Chancellor, sir. Professor Kodareddy sir is Vice Chancellor. He himself is a professor of mechanical engineering. Under his direct supervision, very particularly, this School of Mechanical Engineering is trying to equip itself in extending wings from this academic year very particularly. So far, the Dean pointed out the number of scholars, students, and activities all at one side. Henceforth, the future shape is going to be different and vibrant. I'm sure under the benign guidance of our Vice Chancellor, sir, this workshop will be successful, and the days to come also will be very bright for the School of Mechanical Engineering. Thank you, sir, for your valuable guidance in this occasion. And I am equally thankful to all the participants, resource persons importantly, who are going to be with us for 3 days in delivering the tools and techniques, in training the people in various ways in material processing and 3D printing. Really, the title itself is an opportunity. It's a 3D printing opportunity, really is an opportunity. Please make use of this opportunity and learn and apply. Our VIT-AP's motto is also apply knowledge and improve life. All the efforts, whatever initiated by the institute, are for the benefit of the nation at large. With this vision, VIT is always taking lead and marching past towards the success of every individual, with the connotation of VIT universities, share and care. Whatever we learned, we shall share with the people, and we must see that they are taken care. With this, and particularly, without saying something about our today's esteemed chief guest, I am unable to keep quiet. He said in the beginning, our Vice Chancellor sir chased him. Sir, you happen to see, the participants, please listen here. All of our graduates, after while completing the BTech, if they get a job in the Tata company, Mahindra company, Nissan company, and so on, in the core engineering company, being mechanical graduates, they all feel very pride, right? Yes. Great companies, Mahindra company, Nissan company, right? Tata company. For those companies, Jayasima Reddy sir is behind. He is supplying successfully all auto parts for these companies. Sir, how can we keep quiet without chasing you, sir? Sir, VC sir rightly identified you, sir, for our university here on this occasion. See here, he is not only doing business, dear participants. He is a great entrepreneur, having educated in the US, George Washington University, in the mechanical field, and this particular subject he learned and he returned. He is really a true son of the soil of India. Very great to have with us today's chief guest, Jayasima Reddy sir. All your efforts are definitely going to be useful to our university, sir, particularly the mechanical engineering students in the 3D printing sector. Sir, we will be inviting you in the days to come, and we will have you in the university board on various aspects to make use of. You said you make use of the opportunity of this workshop. We will be definitely making use of your expertise in this university, sir. Thank you very much for valuable input. Today's chief guest is also a special person to say, and every year I'm proud. He is helping the central government in the implementation of the project of the central government, Beti Padhao, Beti Bachao, by helping poor girls in their higher education, by supporting them through NGOs. How many of us will be having a consciousness like this, with civic consciousness, helping the poor? Sir, really, our heartfelt pronouns to you for your support and solidarity towards the downtrodden and deprived. A technocrat is always a technocrat. Here, chief guest is not only a technocrat, he is a great humanitarian. We are all proud to have with us the chief guest today, Jaisimha Reddy sir, and his knowledge is going to be with us, and his techniques, his intellectualities and techniques will be with us. And I appreciate and congratulate all the participants participating in this 3-day workshop from 15 states, representing various IITs, NITs, and state universities, technical universities. I'm sure this 3-day workshop will be definitely fruitful and useful in their career. Every one of us is expected to learn every day at least one. Similarly, our VIT's AP is always putting efforts in sharing the knowledge, bringing the various people from the globe to VIT AP. That is how VIT is very promising institution to all the graduates, parents, outside stakeholders. Thank you very much, sir, for giving me opportunity to talk on this occasion. I sincerely thank all the participants and congratulate them that they'll be having very good learning during this 3-day workshop. I thank Madam Dr. Rakhi for giving me opportunity, and I'm also thankful to the PR department of VIT AP University for taking this workshop flashing in the media. Thank you very much.
Thank you, sir. Thank you for delivering the vote of thanks and addressing the gathering, sir. By this, I think we can conclude this inaugural session. And once more, I would extend my heartfelt welcome and a warm welcome to all of you present here to this 3-day workshop in advances, online workshop in advances in material processing, 3D printing and opportunities conducted by School of Mechanical Engineering at VIT AP University. Thank you. Thank you all. I would hand over the session to Dr. Pankaj Tambe. Sir.
Okay.
Thank you, Jaisimha sir.
Yeah, thank you, sir. Jaisimha, sir.
Thank you, everyone. Thank you, sir.
Yeah, thank you, sir.
Thank you.
Dear participants, we will meet in 10 minutes. So be online. Professor Ambu Sharma will be now the host right now. I'm just making him host. I will come back in 10 minutes. Okay, Rakhi ma'am.
Thank you, sir.
Okay. Uh, Good morning to everyone. I think Dr. Divya Padmanabhan has joined. Ma'am, you have joined? Yes.
Yes, yes. Good
So we
morning,
will
sir.
start in another 5 minutes, ma'am.
Okay, sir.
I think we need to start. Good morning, everyone. I welcome everyone, and I welcome Dr. Divya Padmanabhan. Madam, are you?
Yeah, I'm
Madam, are
here,
you
very
here?
much here. Yes, yes.
Okay. So first of all, what I will do is I will brief about your CV. I have already made you a co-host. Dr. Divya Padmanabhan is now currently a professor in uh, Department of Automobile Engineering, Pillai College of Engineering, Navi Mumbai. She did her BTech from VNIT Nagpur. Formerly, it is Vishwesvaraya Regional Engineering College. and MTech and PhD from IIT Bombay, the same department. I did my PhD, metallurgical engineering and material science department, and her area of research is ceramics, polymer composites, and she has published many papers, and she is the recognized postgraduate bride in Mumbai University. Over to you, ma'am, for the session. I hand over session to you.
Thank you, sir. Thank you for the introduction. And let me start to share. Please let me know if you are able to see my screen. Are you able to see my screen? Please let me know.
Yes, ma'am. Yes, now we can clearly see it.
So a very good morning to all the participants. And I was there for the inaugural, so I think Kota Reddy sir has already left the meeting. But I'm glad that I had met him, like he being a resource person in one of the programs that I attended many years back. So at the outset, let me thank Dr. Pankaj Tambe for having given me this chance to speak about additive manufacturing, and a focus of this talk would be specifically the metallic systems. So here, the audience, Pankaj sir, if you could help me in the audience, are there research scholars working in the field of additive manufacturing?
There are research scholars, there are faculty members from various colleges and universities.
Okay, okay. No, those who are particularly working in the field of additive manufacturing, if you have any idea?
Yes, there are a few faculty members. They are working in additive manufacturing and research scholars.
Okay, okay. So let me, this being the first talk of the session, I have preferred to keep this session more of an introductory kind of a thing. And so let us get started with this topic, that is additive manufacturing. Now, since most of you are from a mechanical engineering background, I think you have fair enough idea about what additive manufacturing is all about. So typically they say that this additive manufacturing, it's not one process, actually it's a group of processes, which we'll come to us as we move on in the presentation today. But it's defined as a process to make objects, and these objects are created from the 3D model data that has to be available for the object that we intend to make. And this building up or creation of the object is usually achieved layer by layer. Okay, one layer formation, on top of it another layer build up, and then this goes on till the entire object is created. So additive manufacturing is the process of making objects from a 3D model data, usually layer by layer, as opposed to the other manufacturing technologies, as opposed to the traditional machining or subtractive manufacturing methodologies. So here, now one of the reasons for this, the additive manufacturing gaining so much importance is the freedom that it gives with respect to the design. If you can think of a design, you can make the object by the additive manufacturing process. So that's the major, that's the biggest advantage of additive manufacturing technology. That is, it gives you there is freedom, ample of freedom with respect to design. You can even say that there are no constraints as far as the design of a component or an object goes. And in the last 10 years, the additive manufacturing as a domain has picked up hugely. And in different universities, different subjects have been introduced by different names. Some of the names which are used to identify the additive manufacturing technologies, they go by the name of rapid prototyping. Rapid prototyping was the name with which this technology was earlier first identified, rapid prototyping. In fact, even today, many people prefer to call these different approaches as rapid prototyping techniques. The other name, 3D printing. 3D printing is also kind of becoming synonymous with additive manufacturing. Many times, rather than specifying a particular method, we just say 3D printed. So 3D printing, rapid prototyping, rapid manufacturing. In fact, in my university, we identify this as rapid manufacturing techniques or technology. The other names for the additive manufacturing, they are layer manufacturing, freeform fabrication, direct manufacturing. And in fact, this list is not limited to the 6 names which I have put in here. So as a begin, the difference, or what is it that primarily differentiates these additive manufacturing techniques, technologies from the traditional manufacturing routes? It is, if I say, if I try to categorize traditional manufacturing into categories like formative and subtractive, we, since most of the students, faculty here are from mechanical background, I'm sure all of you understand casting technology. All of you have learned about production processes. You know the production processes like rolling and extrusion, bending. So when we are talking about the formative manufacturing technologies, okay, the shape formation occurs in a constrained environment. Okay, typically casting, if I say, yes, it's definitely forms a form. I mean, we from a liquid, it is, I mean, that's a little more different, but from a liquid, we try to achieve solidification within a contained, in the mold, typically a mold, and you have the solid object prepared. So you're forming, that's forming. Okay. In fact, all those processes wherein deformation is involved, when we are trying to manufacture certain components and there is deformation involved, like the extrusion process or the rolling process, all those are also, I mean, they can also be clubbed under the formative process, the formative manufacturing category. And another traditional approach of manufacturing, it is the subtractive manufacturing techniques. Now, subtractive is whatever we do in our workshops, lathe machining, with a lathe machine, milling, grinding, cutting, boring, drilling, any operation that we generally normally do in the workshop, that could be called as a subtractive manufacturing process. Subtracting, from the terminology, it's very clear. We are subtracting the material, when in trying to, in our aim to create an object, a solid object, we are trying to subtract what is not required. Okay, so that is subtractive manufacturing. From the schematics, I think it's pretty much clear that stepwise, the shape formation is achieved by way of material removal. And if you note the starting material size and the final object which we have created, it's very obvious that the final object has reduced in size significantly as compared to the starting volume of the material. Okay, this is one of the main characteristics of the subtractive manufacturing methods. Okay, as the object gets formed, there is a huge reduction in the volume which is happening, and accompanying that is a huge amount of material removal. That means losses, material losses are huge when we talk about the subtractive manufacturing techniques. Whereas now, when we talk about this new category, that is the additive manufacturing, since we are creating layer and then building up the object, okay, how much of the layer is being built? It depends on what is the object we are trying to create. So in that sense, the material removal, or not the material removal, the material losses, there's no material removal happening in case of additive manufacturing. There are minimized material losses. Very little loss in terms of the material happens during these additive manufacturing process. And the name additive is simply given because the object is created by addition of layers. Adding layers one after another, that is how we create objects in all these methods or techniques that come under the additive manufacturing approach. Okay. So let's have a look at this, briefly a look at the history of this additive manufacturing. And in fact, like if I talk about the history of rapid prototyping, it dates back much earlier, much earlier. But then if I'm talking about the additive manufacturing, Chuck Hull is famously recognized as the one who invented the first of those techniques which come under additive manufacturing, that is the stereolithography. But even before 1986, there have been publications with respect to the approach which we identify today as additive manufacturing from Japanese researchers, Kodema and all. Okay, and then once this, but then I would say 1989 was the time when the first commercial form of additive manufacturing happened, and since then there is no looking back. In fact, every day you look up and you see some new development in the field of additive manufacturing. Existing technologies are being improvised, or people are trying to come up with still better ways, yes, to incorporate layer-wise build-up of objects. And some of these remarkable, some milestones which happened in the field of additive manufacturing, SLA printer in 1992, and other things. Okay, this RepRap, that's an open source kind of a platform which came in 2005, and many such things have come up since then. Okay, in fact, this entire additive manufacturing, people trying to think about creating objects by layer-wise addition, it all began with the finding that it is possible to solidify polymers by exposing them to UV light. And in fact, I mean, that was the basis of all these additive manufacturing processes which came earlier. And now, of course, in order to accommodate for different types of systems, material systems, many more processes have evolved. If we talk about the applications, huge, okay? In fact, I would say that you talk about a domain and there is something, some object in every domain where, where additive manufacturing has made its entry, okay? To talk about some of them, aerospace heavily, aerospace is one industry where additive manufacturing is it's already being used and explored heavily. Okay, one of the, okay, I'll come to that later. Another area is that of medical, in the biomedical industry, in the form of implants, sir, the chief guest today, he mentioned about medical implants and all. So medical implants is one big area where additive manufacturing has already shown its capabilities. Transportation is another area. Transportation may be in the form of two-wheelers, in the form of four-wheelers, everywhere. Yes, additive manufacturing is being tried out these days because of the whole lot of advantages that it has to offer. Energy sector is another one. Consumer products, definitely. Jewelry as well. In fact, I must point out that, about 18 years back, very much here in India, the first of these RP machines which came in, at least in this part of India, in Mumbai area, it was for the purpose of jewelry making. Okay, and then it was also displayed in one of those exhibitions which Godrej Industries normally has, and there was such a huge lot of students and faculty and entrepreneurs. Everyone wanted to see what this RP machine is. Okay? So those are some of the areas where additive manufacturing has already shown its capabilities. Now, I mean, this additive manufacturing techniques, it is known, or it is being identified, I mean, it is being said to be a disruptive kind of a technology. Okay, so what does this disruptive technology mean? Okay, we'll have a look at it. But I am sure all of you also identify additive manufacturing as one of the major contributors to the fourth industrial revolution. Okay, so the reason why it is known as a disruptive technology is See, for that matter, many technologies have been named as disruptive technology. In fact, from an innovator's perspective, they define a disruptive technology as one which is able to impact maximum people or maximum domains. So in that sense, definitely yes. As I had said a few minutes back, you name one domain, name one area where additive manufacturing is not being used, it will be difficult for any one of us to answer. It has entered into every aspect, technology, normal human, consumer goods, technology, anything, big technology, anything. Okay. In fact, the reason for it being disruptive technology, another reason I would say that, yes, it has definitely, this has a potential to impact huge amount of people's life, definitely. And the kind of impact that it is making it's in a positive way, to say most of it. But at the same time, in certain regions, it has made things difficult because of the way that the additive manufacturing process is. Many a times, the process chain, the traditional process chain of making of manufacturing, if I say it was a huge process, you would want to stack on the inventory. You would want to stack up on the inventory. You would have to build facilities for the manufacturing, capital investment and all that. Then you would have to train people to use your capital. And then you will have to make arrangements to stock and then also transport your manufactured goods, right? So such things, if you see, that kind of a requirement is not seen with this additive manufacturing. In fact, it is that in that sense, it's a fast process. I mean, through a very short time, you can achieve the making of a complete object. So that means there are many, because of the way in which the additive manufacturing technologies have been developed, and a lot of it is automated. So what happens is, because of that automated nature of manufacturing, there is a loss in terms of employability too. Okay, so in that sense, this technology has been named as a disruptive technology. But on the other side, we do have to remember that the kind of impact it is making, it is huge. Okay. The design constraints are almost eliminated with these processes, which we could now look into under additive manufacturing. I mean, as I said a little while back, if you can think of a design, you can have the part made. Okay, so allows this is something which complex geometry can easily be prepared with no additional cost. So, and the speed at which an object can be made, okay, it is quite high, and I mean this leads to a reduction in the lead time also. You have the digital form of your object ready, and you have to give it to the machine. I mean, you have to feed it to the machine, and the part gets made. Okay, so in fact, except for the machine requirement, the printer requirement, when I say printer requirement, as said, there is no tooling requirements which are expected with most of these additive manufacturing technologies. You can be assured of the dimensional, the dimensions of the object that we are trying to create. In terms of the material usage, I've already said the losses are, I mean, the losses meaning the material losses which happens during the manufacturing processes, the traditional one, that is huge. Whereas here, there are minimum losses with respect to the materials. At the same time, I must say that with newer technologies coming in, the kind of materials which can be 3D printed, that's also growing day by day. You have different kinds of materials, different combination of materials which can be 3D printed. So it's also said to be a clean technology with minimum waste, and most importantly, a shorter learning curve is what is associated with additive manufacturing technologies. this shorter learning curve, this actually means, see, if we talk about a process like rolling, okay, or an extrusion process, okay, there is capital investment to create those facilities. One will also need to equip people who are skilled enough to operate those machines. Okay, in that sense, there's a lot of expectations with respect to skills are huge when we talk of traditional manufacturing approach. Now, with this additive manufacturing approach, the process is pretty much automated, and in that sense, the learning curve, the amount of time that a person would need to start actually doing the manufacturing is very little. He doesn't have to learn too many things. It's the operating the, one has got a basic idea about how to create a CAD model, and then the 3D printer, the use of the 3D printer. So it's the learning curve, the entire learning curve, the time required to build up skills, it is significantly reduced in additive manufacturing. In fact, I must point out that today in many of the developed countries, printers, 3D printers, people have it at home. And who are the ones using those 3D printers? The children. Okay, children as young as 10 or even below 10 years of age, they are using it with so much of ease. So it doesn't require too much of a skill. So in that sense, this technology has actually led to a shorter learning curve. Let us just quickly have a look at what are the major, where are the major markets for 3D printing? Yes, you can see here, this is from the, there's an annual report, the CAGR annual reports projected for the 2018 to 23. You see that US is the market size of 3D printing in the US, it is in terms of $7.5 billion. Okay, the expected rate, the expected markets. Okay. And another thing I must just, as we talk about 3D printing, we do not find India featured here. So you all would have understood that we are still at a very primitive stage as far as 3D printing goes. Okay. So we have, in fact, we can take it the other way. There is an ample of scope. There are lots of opportunities to do work or enter into this field of 3D printing, maybe in the form of an entrepreneur or in the form of a researcher. And on the right, you see the graph there, the sectors, the industrial sectors where additive manufacturing is being used. As I had been telling, you talk about a domain and you find that additive manufacturing is already in use there. You see maximum contributions from electronics and consumer goods, motor vehicles, automobiles. That's another area which is picking up day by day. Medical, yes, there it is 15%. Aerospace, another big market for the additive manufacturing technologies. And even otherwise for the heavy industry, for academic institutions as in the form of a research or a startup, again, there is a small contribution there. So, okay, it's written architectural, which is 3%. Now, to add to that, I would just say that even construction is one area where this is picking up. Now, you have, people have developed huge 3D printers which are capable of, printing concrete mixtures. And in that sense, the entire time taken to build up a house reduces significantly. Okay. Another, this is the expected, it is expected that this region, the Latin American regions, and then also the Asia Pacific, the African regions, this is where maximum growth is expected in the next, in the range 2019 to 25. So we expect that even we would find good chance to do something on the field with respect to 3D printing. So this is another, okay, I will not actually touch on this, but then I'll just say. So let's now come to what this additive manufacturing is all about. I hope everyone knows by now that here we are talking about creation of objects by layer-wise deposition of the material. Now, typically, there are 8 steps which define the process through which any 3D printed object has to be produced. First and foremost, you need to have that object in a digital form. Now, when I say a digital form, we need to have the object, the CAD file, a 3D model. Okay, a 3D model of the object is the first requirement if we need to have it 3D printed. So if I'm able to create a 3D model of an object, I should be in a position to create that object through any one of those 3D printing technologies. So the first step is where we have the where we make a 3D model, the CAD file. Then the CAD file is something which the computer definitely identifies, we also understand, but it will not be actually identified by the printer, the 3D printer. So this CAD file, I mean the 3D model which we have created, it has to be converted into an appropriate format. Now that format is typically known as the STL format. And so every 3D model has to be converted into an STL format. And then this STL format is fed into the 3D printer. Now the 3D printer, again, because we understood that it is layer-wise formation. Matlab, to form every layer of an object that we are trying to create, there has to be some data which the printer is able to identify. So this STL file will again be converted using an appropriate software. Typically, it's known as slicing software. And every machine has got a different kind of a slicing software, because to build each layer, there has to be a layer. So it's a planar thing, right? So if it has to be sliced, the entire STL file which we have created, it will be sliced layer by layer. And that is what, that the sliced layer is what is going to be executed when the command is given to the machine. So the file transfer to the machine, followed by the machine setup, and then we start building. Okay, then we start with creation of the object. Okay, when the object gets built up completely, then we remove it from the platform. And in most cases, a small post-processing may be required. And once the post-processing is all done, the object which is prepared is ready to use. So again, the same thing, step 1 to step 7, 3D model creation, and then you have the STL file. Step 1 is the 3D model creation, followed by the STL file creation, which is then transferred to the machine so that the slicing occurs. Then the machine has to be set up to build the object. And now the pictures that you see on the right, the first model the first picture that you see, that's the CAD model. Then you see the second picture there, that's the STL, the CAD model has been converted into the STL file. And from the STL file, once the object has been created, that's the print. The last picture that you see of the cup, it's the printed object. There are many parameters which would actually decide how good a part has been created by the 3D printing method. Okay, how good in terms of how is the strength and what is the quality, and strength and the quality again to some extent would also decide the cost. Of course, the raw material cost is also something which will ultimately decide what the final cost of the 3D printed part is going to be. So in terms of the parameters which govern the 3D printing processes, there are something which are known as slicing parameters, and there are other parameters which go by the name of printing parameters. So when we are talking about the slicing parameters, first and foremost, it's the layer thickness. Okay, because we have understood it's layer-wise addition. So what is the layer, a single layer which is being created? What is the layer in the sense? What is the thickness of the layer which is being created? Then you have the width of the extrusion. Okay, then you have the infill density. I mean, these are all parameters which need to be set up in terms of, when we set up the machine, these are the parameters which are crucial. Okay, then infill orientation, the infill pattern, because the way the infill has been created, that will decide the, one of the things that is decided is the density, which will definitely affect the overall strength of the part which is being created. Then the orientation of the part, the support density, if there's a support required for the object which is being created, the density of the support, what kind of an orientation the support has. Okay. Then other parameters, the printing parameters, something like what is the temperature at which the printing is being done, what is the cooling power of that particular machine, what's the temperature of the platform, the build plate, and what is the speed, the scan speed at which the printing is being done. Some more, if you look at the same parameters once again, we talked about the layer thickness. Now, when the layer thickness, what happens is that the properties of the material would not be the same in case of 3D printed objects. Typically, it is observed that in the direction of the printing, the strength is going to be high. But if you look at the Z direction, or the direction in which the thickness was built up, it is going to be weak. So this analogy is something similar to what we also learn with respect to orientation of fibers in composite systems. Okay, so layer thickness, in terms of that, the thinner layers would result in a higher surface finish, but the part build time proportionally increases. And also, when we have thinner layers, if you're able to create thin layers through a particular approach of 3D printing, then we can produce intricate details and also sharp corners in that object. With respect to the extrusion width, if you have the extrusion width, it's too close, then it is quite likely that two adjoining layers are going, there is going to be an overlap. And if it is too far off or too distant, then it is going to result in a gaps in the material flow. Okay. So thicker parts are required for better bonding as well as good mechanical properties. Okay. Infill density, you can look at that picture. I'm not sure if you're able to see it very clearly. It is, normally when we try to create an object, it's the outer surface which is, which is first deposited. So we can call it as a shell. So the outer shell is solid, whereas the interior sparse material is, you have an option to reduce the material inside. Okay, so that is what infill density, that's why one of the parameters which we need to set is the infill density. You can produce a part which is dense if you give a higher infill density. You can even produce parts which are less denser by providing a lesser amount of infill density. But again, in fact, one of our students did a project where he tried to find out the relation between infill densities and the properties that the 3D printed object had developed. Okay. So infill orientation, the pattern and the part orientation is another thing, another important parameter which will finally decide the quality of the product. I will not go much into the details of it. And okay. So now with that basis for what additive manufacturing is all about, I'll come to the processes directly, and towards the later part of my presentation, my focus would be on metal additive processes, metal additive manufacturing processes. So this is a classification which you see on the screen, which is based on what kind of material are we starting off this additive manufacturing with. Okay, it could be classified as liquid-based processes and powder-based processes. Now, the principle that most of the liquid-based processes are based on, it is based on either fusion or polymerization or solidification. Okay, so under this, in fact, I will not go much into the classification further down, but we'll look at this still on in the further slides. Whereas for all the powder-based processes which have been categorized under additive manufacturing. The principle which forms the basis of that solidification or object forming, it is the process of, the fusion or binding. Okay. And there are many processes which have been developed wherein it is the fusion which happens that leads to the formation of the solid object. And there are also processes where the primary source, or the primary mechanism through which the object is created, it is by way of binding. In fact, these days, many a times we come across this additive manufacturing, rapid prototyping, classification based on what is the form, the starting material is in what form, whether it is in a liquid form or a powder form, sheet form, gas form, whatever it is. And then there are many, many technologies which have emerged, many additive manufacturing processes which have emerged to take care of liquid starting phases, solid starting phases. Again, solid, you could have different types of starting forms for the solid materials. In fact, ASTM, they created a committee, F42 in 2009, and what they came up with, this is a classification which is more or less, this is more standard, I would say. They have categorized into 7 groups. They have categorized the additive manufacturing into 7 groups. First one is a powder bed fusion. The second one is the directed energy deposition. We'll have it may not be possible to cover each and every manufacturing, additive manufacturing process, but still I'll try to touch upon most of them in the subsequent slides. Powder bed fusion, directed energy deposition, the material extrusion process, vat polymerization, the binder jetting, material jetting, and then sheet lamination. Okay. Now, if you look at the last column there with respect to materials there, you see metals, polymers, photopolymers, polymers, sand, metals, polymers, waxes, metals, paper, and all. What is missing there? It is ceramics and composites. Now, as you are all from mechanical engineering, I presume all of you know the different classes of materials, because apart from metals and polymers, also there are very important classes of materials. That is the class which goes by the name of ceramics, and yet another very important and emerging class, that is composites. Okay, so here, in fact, of course, it's not listed here on the table, but let me tell you that it is possible today to 3D print ceramics, composites, metals. Of course, it's written, but please understand, when we're talking about metals, it's the entire metallic system that we're talking about. Pure metals as well as alloys formed from metals. Okay. So in the powder bed fusion processes, powder bed fusion is not one single, it's not one single kind of, there are different processes or different types of technologies which have emerged from the basis, from the basic powder bed fusion technology. What happens there is, since the starting material is in the form of a powder, there has to be some mechanism by which the powders can be fused. And that is achieved by way of providing thermal energy to the powder. How to provide that thermal energy? There are different ways, and that is what we'll see in subsequent slides. There's another approach wherein the directed energy deposition approach, most suited for metals, wherein again, there is, a focused thermal energy is provided to bring about the fusion of the materials. Then you have processes which are based on the extrusion process. Okay, material extrusion, the category is known as material extrusion. Very popular, hugely popular method of additive manufacturing. In fact, some of the cheapest 3D printers, at least in India, they are all based on this material extrusion process. And in fact, that's why we see that even many colleges, many universities, they have procured 3D printers, and at least the ones that have, they'll definitely have one which is based on material extrusion. Then you have some specialized kind of processes, that is vat photopolymerization, wherein there's a use of a photopolymer, and the starting material has to be in a liquid form, and that liquid photopolymer is made to harden, made to cure actually, by subjecting UV light onto it. There are other technologies like the binder jetting method, material jetting, and also the sheet lamination method. So I'll move to the Next slide here. Now here you see the 7 classes which was given by ASTM once again, the VAT photopolymerization, material jetting, material extrusion. Now, these 3 processes may not be directly useful for additive manufacturing of metals. It doesn't mean that no one does it. Yes, people are trying out different methods, some DIYs, some approaches on their own to make use of metals in these processes. But normally it is not meant for metals. Okay, indirectly you can one can have metals also 3D printed, but the 4 names that you see on the right, binder jetting, the powder bed fusion, sheet lamination, and the directed energy deposition. These are the processes where metals can directly be 3D printed. Okay, when if you recall that history slide which I presented some time back, okay, it all started with the SLA. SLA, it was a process it meant for 3D printing of polymers. So even today, polymers happen to be a big group, a hugely popular group as far as 3D printing technologies go. But in the last 10 to 15 years, many technologies have emerged which allows the printing of metals, alloys, ceramics, composites. In fact, when I say composites, different kinds of composites, it's possible to have them 3D printed, okay, by one of these binder jetting or powder bed fusion or sheet lamination or even directed energy deposition methods. And this is a very, exhaustive standard structure of the additive manufacturing process. If you see here, what kind of feedstock materials can be 3D printed? I have already mentioned metals, ceramics, polymers, composites, and in different forms, everything possible today. Again, now let me be very specific in terms of these. I said metals and alloy systems as well. So titanium alloy powders, there are lots of research groups which are working with titanium alloys, 3D printing of titanium alloys, particularly for biomedical applications. Then you also have steel rods, then you have ABS filament, nickel-based alloys. Okay, and these materials normally find applications in aerospace, automotive, and medical industry. Nickel alloys, titanium alloys also, for the lightweightedness which is associated with them, they have huge applications in the aerospace industry. With respect to the processes, we've already talked about it, those 7 names there. And okay, so more, as I move to with respect to the finished parts, yes, post-processing is required and also testing may be required. And particularly when we're talking about the biomedical applications of 3D printing, the parts, the implants which are produced by way of 3D printing, it's very necessary to validate them in terms of their biocompatibility before it can be really used in a human body. So all these, lots of groups are working on these systems. So with that background about, what the additive manufacturing is all about, how does the process, how can one execute, what is the process through which a part can be produced, and what are the standards and what are the different process categories? I start with the first of these approaches to 3D printing, which goes by the name of stereolithography. In the history slide, if you recall, again, this was mentioned there, the SLA. Okay, SLA, in short, it's SLA, stereolithography. This was commercialized by the 3D Systems Inc. in 1988. Okay. Now, the features about this stereolithography is that it starts, this is also known as a liquid-based process because the starting material has to be in a liquid form. Okay, so the starting material has to be in a liquid form, and again, in that liquid form, when we talk about, it should be in a photosensitive polymer. If you look at the schematic, you can see there the container holds the liquid polymer, and the it holds the liquid polymer, and the platform, the build platform, or the platform that we talk about, the platform is where we start to create that 3D the object. Okay, and how do we achieve that curing or solidification? My starting material is in a liquid form, but then when I'm trying to create an object, I need to have it solidified. So how is that done? That's achieved by way of a laser beam. The laser beam is made to move on the XY plane. Okay, it's at the 2D plane, on the XY plane, according to what the CAD model has. Whatever the CAD model was created, it always, any process starts with the creation of a CAD model. So the laser beam will raster over that layer to form the shape which the CAD model had, and it creates one layer. When the laser moves through that XY plane, the shape has formed on that one single layer. So one single layer which has solidified, that is typically for the SLA technique, 0.076 to 0.5 millimeters is the order of thickness which is created. The scan speed of the laser is 500 to 2500 millimeters per second. In fact, many companies have now come into making similar machines. So each one has got a different capability with respect to the scan speed. And this way, one layer created, so the platform, then it will move down on the Z axis. The thickness of the object is being created on the Z axis. So the platform is moving down as the object gets created. As the object is built on the platform, the platform is lowered down in order to accommodate for the rising or the growing or the building object. Okay, so that's how typically an object is made by way of the SLA technique. Now, normally what happens in this SLA is that the part which has been cured by the laser, that is not fully cured. Okay, about 85% of curing has been achieved during the process. During the process when the platform moves down and the height of the object is created. But it is normally recommended that final curing be done after the entire part has been built. And that is normally done in an oven. See, 85 to 90% of curing is achieved as the part gets built up. But then the final curing is recommended to be done in an oven. And again, there are ways to find out what is the thickness or what is the time taken to create a single layer. And if I know what is the time taken to create a single layer, and if I know the total thickness that is required, I can find out the total build time. Now, in order to calculate the total build time, what is most important is I need to know what is the area on which the laser is moving, and what is the scan speed of the laser, and also the spot size, or what's the diameter of the laser. So, having seen this, I would want everyone to have a look at this SLA 3D printing being done. In fact, in our college also we have an SLA machine. We also have an FDM from Ultimaker. So I'll proceed with this video. Please have a look at it. So I guess you would have understood what that stereolithography, I mean, how it works. You would have understood that better having seen this video.
One question, ma'am. As we are using the heat treatment, more or less equal to heat treatment where we are using for the processing. In that case, how the material properties can be attained? Is it is constant, or the material properties can be changed, or how it will be?
So can you repeat?
Yeah, ma'am. As we are using heat treatment, more or less equal to heat treatment in stereolithography or some other 3D printing machines for polymers or any filaments.
Yeah.
But the thing is, if you are using that heat treatment means, how you can achieve or attain that particular properties of the materials, so that
Okay. It will always, sir, these UV, the photopolymers suppliers normally, they will recommend up to what temperature you can go for. So that is all standard in the sense that if I have a particular kind of a photopolymer, normally we get it with the instructions, you cannot go beyond certain temperature. So I can set my operating parameter, I mean, the machine parameter, I can set it in such a way that the property of the material doesn't get degraded.
Yeah, ma'am. If you're going,
this is what you were asking, no? You were saying because we have introduced laser beam, we have subjected laser beam onto the polymer, does it get degraded? Something like that is what you meant, right, sir?
Yes, ma'am. Correct, ma'am.
So have I asked?
In that way, is there any particular handbook available for additive manufacturing or 3D printing, so that the exact temperatures and or other things are available in
about the handbook? I'll let you know, sir. But as of now, I don't think there's a handbook available. But every supplier of this photopolymer, they will provide that information in their specifications, product specifications.
Yeah, in that product way, we can have a lot of information from the producers. But in a particular thing, we are going for a particular material means we are going to choose a particular 3D printing machines, or we are going to produce that 3D printing machine. In that way, how and in that way, in material processing, I'm asking, is there any particular handbook available so that we can only use this way material for a 3D printing texture?
No, sir, because standards and all for 3D printing are still not so much formalized as it has been done for other technologies.
Yeah, thank you.
Do we take a break or should I continue? Pankaj, sir? Okay, then I'll continue then.
What we can do is we can take a 10 minutes break.
Okay, fine.
And then we can continue after 10 minutes. You can keep the slide open, ma'am, no issues.
Okay.
So we will meet after 10 minutes.
Sure, okay.
Dr. Divya, we can start now.
Yes, yes. Yeah. I saw some questions on the chat. I'll take them up towards the end. I hope that's okay. So I continue. We have just looked at one of the first additive manufacturing processes that was developed, the SLA technique, which primarily makes use of a liquid photopolymer to start with, and then it is made to cure and set and solidify into the solid object that we desire to have. The next technique under additive manufacturing, again, this is based on starting material being a liquid photopolymer. This goes by the name of solid ground curing, the SGC technique. This was developed by the Cubital Systems, which uses a UV lamp, not a laser beam. In the previous one, in the SLA technique, it was a laser lamp, it was a laser light, which was enabling the curing of the photopolymer. Here it is a UV lamp, which is focused onto the part, onto the object which we intend to form. But the technique is based on the use of a mask. There's a mask which is arranged on top of a glass layer, and the mask it's like a the purpose of this mask is allow the UV light to get onto the part which should be set. The shape formation is achieved by way of the UV light being exposed, being focused onto the exposed part of the polymer. So you can see the steps which are shown there. Step 1, there we have the mask ready under the glass plate. And then the step 2 there, it's the liquid photopolymer. On the liquid photopolymer layer, the mask is kept. This assembly of the mask and the liquid photopolymer is subjected to the UV lamp. Based on the mask, the UV lamp is not really getting exposed to the entire photopolymer liquid. Certain areas are only getting exposed, and only those areas would get cured. The rest of the areas will remain unsolidified. So those unsolidified or uncured photopolymer can be wiped off or it can be cleaned. And then we start with the next layer. That is how the layer-wise formation is done. Now what happens in this is, as one layer is formed, the rest of the liquid polymer is removed. Wax is also, once all those unwanted liquid is removed, wax is introduced into this. So wax kind of acts as a support for the object, and it will keep the object, it will prevent any, the failing of the object during the process of build. Okay. One advantage as compared to the previous technique, it is that there is no post curing required. Everything happens with that one exposed, there's no post curing as such required. If you recall in the SLA technique, there is a final curing of step which is mandated. Such a thing is not required here. But I would say that even if you look at all the publications and whatever work is being done in the field of 3D printing, this is not that popular method. Not many people are really working on this, actually speaking. The next one, the droplet deposition manufacturing method of 3D printing. It also goes by the name of DDM. Now, I'll be quick with this method because the starting material is a material which should be in a, we should be able to have the material in a melted form. Okay, that means polymers, waxes are most suitable in order to do this in order to 3D print using the DDM approach. And also low melting metals can also be 3D printed using the droplet deposition manufacturing approach. What is basically done is that small droplets are deposited to the previously formed layer. Now what happens when we say droplets, these droplets are very, very fine droplets, and the rate at which these droplets are deposited, it is very high. Something like, 8,000, 10,000, even more than 10,000 droplets are deposited per second. So many droplets coming onto a layer. And then once the droplet has come onto a substrate, it will spread out. And as it spreads out, it will solidify. Okay, basically that is what is happening in the droplet deposition manufacturing. That's why the name droplet deposition. We are making the droplet deposit and solidify. The deposition of the droplets for each new layer is controlled by a moving XY spray nozzle workhead. So that schematic, it would help understand, what this is about. The green colored is the part which we are trying to make. And there is another blue colored part also, which you see along with the green colored part, which is nothing but a support material. And that support material, once the part is completely done, can be eliminated, can be removed. On the basis of this droplet deposition manufacturing concept, BPM Systems, they have developed what is known as a personal modeler. Now, in this particular printing machine, the personal modeler, there is an ejector head, which has an oscillator, which has a piezoelectric oscillator. And this piezoelectric oscillator, it shoots droplets at that high rate, 10,000 to 15,000 per second. And these droplet size are very fine and also uniform. So as they flatten out, as they fall on the substrate, they flatten out and form solidified layers. So, after each layer has been deposited, the surface is milled or thermally smoothed to achieve the accuracy in the Z direction. That's how the object height gets built up. Typically, the layer thickness is about 0.09 millimeters. So that thin layers can be built up using the DDM approach. And the DDM approach, and in this machine, which is known by the which goes by the name of personal model. So these three techniques which we just saw, the SLA technique, and then the solid ground curing, and then now the droplet deposition manufacturing, these are the most commonly seen additive manufacturing technologies which make use of a liquid to start with. Okay. Now we come to another set of manufacturing technologies, additive manufacturing technologies, which makes use of the solid form of a material to start with. The starting material is in a solid form. And in that, the first one that I would want to take up, this goes by the name of laminated object manufacturing. Okay, laminated object manufacturing, it was a proprietary from Helices, and now many companies have also come up with similar technologies. The starting material is in a solid form for sure. And here, the solid form, when we say it has to be in a sheet form. Okay? So the sheet, if you look at the schematic, you would understand it clearly. There is a supply roll, which will supply the sheet form of the material to the roller. And then on the roller bed, on the bed or on the platform where the shape forming happens, as per the CAD model, what has been fed to the machine. It is again the use of a laser beam. Okay, a laser beam will move on the XY plane on the part as per the CAD model, and it will create the shape in one layer. Then the sheet moves forward, and it is collected by the take-up roll. That means now a fresh sheet has got exposed to the laser, and the laser will once again move on the XY plane and create the shape that the CAD model has read. And that is how layers get formed one on top of the other. So the stock thickness typically for this laminated object manufacturing is in the order of 0.05 to 0.5 millimeters. And it's always a sheet material which is supplied to the for this LOM process. And these sheet material, they have an adhesive backing rolls that can be spooled between the rolls. And these lasers, most of these LOMs have a laser which are carbon CO2 lasers with a with a power of 25 to 50 watts. I would want to show you this video of LOM also. Now, I will not be showing all the videos of the different methods, but then LOM being an important in an important additive manufacturing route, particularly for laminated, if the starting material is solid in a sheet form or a laminate form, this can be used. This initially came up as a method to make objects with cellulose, even cellulose. But now, just recently I was reading something, even sheets of metals have been tried out using this. The adhesive,
Excuse me, ma'am.
yes.
I have one question.
Yeah.
Whatever those 3 vertical elements were there in that video, what are those?
Anti-glue, what yours? This one?
Yes, these 3 one.
They have called it as an anti-glue. Okay. The rolls, they should have some kind of an adhesion, right? Because one, इसमें कुछ actually क्या है, for one layer to bind onto another layer which will be formed subsequently, there has to be an adhesion. Okay, so it has an adhesive layer, but they also, this one, they particularly talk about this anti-glue also. This is probably to prevent sticking between the layers.
Yeah, okay, fine, ma'am. Yeah, thank you.
Ma'am. No, ma'am.
So I hope that was, it's now these technologies have been simplified by many companies, and you just saw in this video how compact this printer was. It was, I mean, it was just the size of a normal paper printer, and how nicely and how easy it was to 3D print this part. So let's move on to the next method. So this was the first of the additive manufacturing methods used, wherein the starting material is in a solid sheet form. Now I come to a very popular method, that is the fused deposition modeling by a proprietor of Stratasys initially. Now, in fact, there are lots of people, even students, college students. We had a group who had made a kind of an FDM machine. Okay, so if you understand what is, how does it work, it is easy for anyone to come up with their own ways to create these machines as well. Okay, so FDM happens to be the most popular technique of 3D printing or additive manufacturing. The starting material has to be in a solid form, and that too precisely it has to be in a wire or a filament kind of form. Okay, because that is the what is fed into an FDM machine. It's a spool, a spool wherein which has these solid filament of the material wound around it. Typically, most machines have a capability to accommodate diameters of 1.25 millimeters, the filament diameters of 1.25 millimeters. Most common material which is 3D printed using this FDM, it is the class of polymers. Okay, in addition to polymers, even waxes are done. In fact, we have a group who's trying to make use of this FDM, the basic FDM technology, to achieve printing of ceramic systems as well. But okay, so there are people who are doing many things simultaneously, but the thing, when we would normally identify this FDM with polymeric systems only. So it is actually based on the process of extrusion. Everyone understands extrusion. Metal extrusion is something that all of us have studied and seen also, many of you would have. Okay, so this works on the principle of extrusion, wherein we make the plastic material, the polymeric material, flow through the nozzle. That means there has to be a setup arrangement, I mean a nozzle arrangement, wherein there has to be a facility for heating. What happens is we have fed the solid filament form of the material in the machine. That will be moved on to the nozzle end. From the nozzle, it is made to melt and come out of the nozzle and deposit as per the shape that is desirable. Okay, so in this case, very similar to the earlier processes also, the workhead, the extrusion nozzle, which is the main, that part of the machine which actually creates that layer, the workhead is controlled in the XY plane, and then the platform would move a distance so that the thickness is created. So that platform movement happens in the Z direction. So what happens is, once the polymeric system has come out of the nozzle, it has been forced to come out of the nozzle in a liquid state. As it deposits or as it falls on the platform, it will solidify. It will get cold welded, it will solidify. And that is the basis of making that solidified layer with the FDM method. Okay, and I'll just show you this one. This is something that many of you would have seen. Now, typically an FDM machine looks like this, what you see there on the left hand side. And the rectangular plate which you see inside, that's the platform on which the the object is built, is created. Okay. Sculptor is the one that I have shown here. Ultimaker is another very popular model. And in India, we find many places have got an Ultimaker make of the FDM machine. And the principle of FDM, I have just, I was just telling you, here it is. The filament is supplied into the extruder head. And then this part will melt the filament, which is polymeric, and it will deposit. And how does it deposit? That is what it will deposit according to what it has read on that sliced layer. And that again, that will depend on what was the CAD model fed into the system. Okay, so that's the basic principle of the FDM. Okay, we have to bring about the extrusion of a polymeric material by way of maintaining appropriate temperature in the extrusion zone. Here again, you know, just like there was a question some time back about the degradation of the polymer when SLA, using SLA. So here also there could be an issue like that. But here, knowing the material specifications, the nozzle temperature has to be maintained appropriately. So that's the FDM. I had thought of showing another video, but then nevertheless, I'm pretty much sure that most of you, if you have seen any 3D printer, in fact, I would want to hear from some of you at least. Have you seen a 3D printer, and what was the 3D printer you have seen? Do you have it in your labs or university or college? You could reply on the chat box if you don't want to unmute. I can see 59 participants totally. Yeah, I got some yes. FDM, Hydral FDM, yes. Okay, yes. That's what, if at least, okay. Bam, FDM, yeah. So you can see here, the participants can also realize that most of the answers that I get here on the chat box, they're FDM. So that is, that's, you can make out that it's such a hugely popular. One of the reasons is simply that this printer is the cheapest one. FDM printers are the cheapest one that you can find around. Okay? And these days, in the last 10 years, the price of these printers have also significantly come down. So today, if you want to buy an FDM printer, you can even get it at something like 35,000. Yes, it is possible. Okay, so that is what I was saying. So most of you, many of you have seen an FDM machine, and if you have used it yourself, you would know this very well. And please try to identify, or please try to go back and try to find understand what was the material which you have seen being 3D printed using your FDM machine. Okay, any polymeric system which we can have it in the form of a filament. In fact, these filaments are even available on Amazon. Okay, it's very easy to procure these filaments of different polymeric systems. But the challenge lies in trying to create a composite system and then trying to create a filament out of it. Okay. One of my groups is working on that. Okay. So fine, I'll move to the next one because my focus would be the next one. Here I come to again another set of processes which are popular for metallic materials. Okay, not just metal, even alloys included. And this forms a big group actually. The first method that I talk about right now goes by the name of selective laser sintering. In short, it's also known as the SLS method. Okay, I don't know if you have ever seen this SLS machine, or do you have it in your campus, your university? Okay, I would expect very less yeses. Is there anyone with a yes?
No, ma'am, no.
I don't see here. Okay, so that means, so the selective laser sintering. Sintering is a term which you all being mechanical engineers have heard about it previously when you learned your topic on powder metallurgy. Okay, so primarily here, this is what we are trying to achieve. We are trying to achieve sintering of powders. So this is a technique which is used when we have the starting material in the powder form. Okay, so in order to ensure that the quality of the product is good enough, the powders are always preferred to be preheated. Preheated just below their melting points, and then you subject the powders, and then you introduce the powders onto the powder bed of the machine, and then make use of laser beam to sinter the powder. The name selective has been given to this technique because we are not trying to achieve the sintering of the entire powders in one go. We are just selectively looking at certain part or certain sections of that powder bed and having that part only sintered. That's why selective sintering. A laser beam is used for the sintering. And again, depending on the material system which is being handled, you can have a whole range of laser beam of different power. Okay. So once a layer has been sintered, then we introduce the next fresh layer of powders onto it and create the next layer. Similarly, layer after layer, we go on creating the object. One thing to remember here is that since the sintering is being done in selected areas, what happens to the rest of the powders around which are there on the bed of the platform? What happens is they just lie there. Okay. In fact, the presence of those powders are helpful because they will actually provide, they kind of act as a support for the object which is being created. Okay. So the loose unsintered powders, as they lie, during the process of the SLS, they help by acting as a support. And then once the entire object has been built up, all those loose sintered powders can be retrieved, can be removed, and you can make use of it once again. So that's an advantage with this. That's kind of an advantage with having those, with this process, it's not wasted. You can use it again. The layer thicknesses which are possible is of the order of 0.075 to 0.5 millimeters. In that schematic, I think that helps you understand what this process is about. The powder bed filled with powder, laser beam selectively moving on to the shape which we want created. Once one layer is created, the roller will introduce the fresh, a fresh stack or of powders are introduced on top of it, and again the lasering, the lasers are focused laser onto the selective regions happens. Now, this is a very popular method for metallic systems, definitely, and also for ceramics, even for composite systems. In fact, I did not introduce this method under the powder bed fusion processes, but I'm going the other way around. In fact, this is one of the most popular of the powder bed fusion processes. Powder bed fusion processes, these are all based, they are all starting with powders and generally making use of powder bed in order to achieve that fusion. Now, 80% of all those additive manufacturing which happens with metallic systems, it is achieved through one or the other powder bed fusion processes, and SLS happens to be one significant one under it. Other processes which fall under this category of the powder bed fusion processes, they're known as the selective laser melting. Then you have the DMLS, that's the direct metal laser sintering process, and also the electron beam melting. So the basis is similar, so I will not dwell too much on it. Quickly, let's have a look at the schematic of each one of it and then move to the next one. See here, on your left hand side, you see selective laser melting setup. Now here again, if you see, it is pretty much similar to what I was just talking about, selective laser sintering. Okay, what happens is in the SLS, there is partial melting or lesser extent of melting happening. It is just interparticle fusion that we are trying to bring about. In case of SLM, the order of the laser which is introduced, that's high powered laser. That's why there will be melting happening in case of the SLM technique. And what kind of powders? It's metallic powders, very popularly done. Then you have another approach under the powder bed fusion itself, goes by the name of electron beam melting. Now, in this electron beam melting, you can understand, the schematic explains to you there. The material is being fed through this feeder. It's in a wire form there. It's in a wire form, not okay. Now, what you have is electron beam, the energy from the electron, high energy electron, when they focus onto the material which is being fed, it will melt. I mean, the high energy of the electrons will cause the localized melting, and that is allowed to solidify. Okay, that is basically the principle of this electron beam melting.
Excuse me, Divya ma'am.
Yes.
Can I ask one question?
Yes.
Concerned with the SLS technology.
Yeah.
Whatever the companies which are there in presently in the market, can you give some feedback regarding any specific companies SLS printer?
I'll tell you, sir. There is one in Pune, and I don't recollect. I'll give you, sir, in a file. I'll give you. There's one company in Pune which they do SLS, they do SLM as well. Okay. I'll give you in a while, sir. I'll just.
Yeah, please. Okay, thank you.
There is one in Pune. It starts from R.
From Pune,
I'll just let you know. Yes, sir.
That will be very fine because.
Are you from Pune?
Yeah, I'm myself working in Pune itself. Oh,
that's great. Okay. I'll tell you, sir. I hope it starts from R. Wrestler or I'll give you, sir, in a while.
Yes, ma'am. Yeah, please.
In fact, I have some 3D printed parts, metal 3D printed parts, which I would prefer to show, but had it been a live, a face-to-face session, I would have preferred to show some of the 3D printed polymers, composites, and even metallic parts. Okay, but then this being online, so that you actually get a feel of how that the 3D printed part is. So you have another powder bed fusion process, the DMLS, direct metal laser sintering. There you see, again, it's based, you start with powders and, quite similar to the SLS, what I have just explained. And I would want you all to have a look at these metal parts which have been produced by one or the other powder bed fusion processes. Okay, that kind of an intricacy and the finish that you have, that you see there on the screen, it is not possible to have it with any of the traditional processes. Okay, I hope everyone agrees to that. In fact, one of those parts, the rightmost part, that's an implant, medical implant made up of titanium. Okay. Just a comparison of these, the laser being the source of energy, powder bed fusion processes, and the electron beam melting process. There are differences with respect to what kind of a powder, what should be the powder size, what should be the processing atmosphere, and what is there a need for preheating or not, that way. So we'll not look at much into the details of it. I am going to share the slide with anyone who wants it. So without going into too much of a details, I hope you understood the crux of what this powder bed fusion is all about. Okay, those who have, I'm not sure, is there anyone who has worked in the field of powder metallurgy? So you will understand that these powder characteristics play a very important role in deciding the quality of the final part. So the same thing here also, the powder characteristics, when I say in terms of the size, the shape, the distribution, they do influence the part property. So 3D printing, we use the word 3D printing so commonly, but actually 3-dimensional printing, it is a patented technology. It is a one specific additive manufacturing approach, wherein again, it is powders which are used for printing, but that consolidation of the powders is not achieved by way of any energy source. as it was being done earlier. No, there's no electron beam, there's no laser right now. What is done here is we selectively spray some binder, no? And the spray pattern of the binder is what is going to decide the shape. No? So it's a layer by layer deposition using an inkjet printer. You see, it's three-dimensional printing. Really speaking, it is based on, it's based on inkjet printing, wherein an adhesive bonding material, which is a binder. No, it's a binder. It is ejected onto the surface layer wise. And then this, the binder deposition, no, that wherever the binder is being deposited, that area will get consolidated. The binder holds the powders together to form the part, while the unbounded powders will remain loose and that can be removed later. After the entire build process is complete, now here, very much like the traditional powder metallurgy approach, the entire build process is done. We have been able to create something like a compact now. This compact has to be subjected to heat treatment or sintering so that interparticle binding is achieved between the powders. Particularly holds good when I'm talking about metal powders. If it is a metal powder, sintering would be a mandatory step. And suppose it is not a metal powder, but it's a powder of some other system, polymeric system or something. In that case, it could suffice with a simple heat treatment step. Multi-jet modeling, yet another process which makes use of powders, but here UV lamp is used in order to ensure the curing. I will not go much into the details of it. Okay. Yeah. This is something that I wanted to talk about. I already know direct metal deposition, one of those 7 classifications given by AST. Okay, direct metal deposition. Under this direct metal deposition technology comes a very famous 3D printing process, also known as the LENS process, the laser engineered net shaping. That's what that LENS stands for. Okay. Now here, what is done is the powders are subjected onto a surface, and these powders are being carried in a gas flow. They are carried in a gas. Okay, so the gas flow along with the gas which contains the metal powders, they are subjected onto the part, and at the same time there's a high energy laser which is used that would melt the part and it will it will solidify there. Okay, so it's a laser beam which is used, which melts the top layer of the part in the areas where the metal is added, where the powder metal is injected into the metal pole, which is then left for solidifying. So this is what is being done layer by layer. The setup is such that there has to be a hermetic chamber to ensure that there is no contamination and to ensure that the part remains absolutely clean. Okay. This is one of these 3D printing approaches which gives very good properties, very good mechanical properties to the part. So this is a beautiful video which shows the LENS process in operation. They'll move a little faster. So I hope you have actually enjoyed and even learned about what this lens process is all about. The beauty of the process, you could note that you could have multi-material systems. You could have different types of materials being fed at the same time. And another biggest advantage of this lens is that you can do repairs. This could be used as an approach to, in fact, what you just saw, the titanium, it was not starting, I mean, it doesn't start on a flat surface. That's we can call it as one more added advantage of this. Whereas you can have different materials being printed together. You can introduce different kind of, two different types of metals or alloys. You can introduce it together into it. So I have some comparisons and all, but I will not really go much into the details of this one because I quickly, okay, the part size, you can just in the direct deposit, direct energy, this lens, what we just saw, it comes under this category of the direct energy deposition, or the LDED. LDED is nothing but laser direct energy deposition process. So it's capable, you can have large parts, heavy parts made, whereas the powder bed fusion processes are more suited for small sized parts. Okay, in terms of part complexity, it is, the powder bed fusion process fares well in the sense that there is any complex geometry, you can have it made very easily as compared to the LDED process. Okay, particle size, typically the kind of particles that are subjected to the powder bed fusion processes, small, fine particles, 10 to 50 microns. Whereas you can have large particles introduced for the for the direct energy deposition processes. And because of these large particle size, the layer thickness which gets developed, it's also on the higher side in case of the direct energy deposition or laser subjected direct energy deposition. You can see it there. The surface finish is good in case of the powder bed fusion processes as compared to the LDED process. Again, that's because of the kind of layer thicknesses which are developed. Okay. Build rate is high for the direct energy deposition process, and it is lesser in case of the powder bed fusion processes. Okay. Scan speeds are very high in case of this powder bed fusion processes as compared to the direct energy deposition process. Multi-material part processing, we just saw it there, and build up can happen on a 3D surface as well for this direct energy deposition, which is not possible for the powder bed fusion. In all these powder bed fusion processes, which we have just seen in a while ago, if you recall, it always starts with a flat surface. So that is some of the comparisons between the the laser direct energy deposition and the laser powder bed fusion processes. Okay, so that summarizes this additive manufacturing of metal additive manufacturing approach of the direct energy deposition techniques and the powder bed fusion techniques, which I have almost talked about as I was trying to cover the earlier slides. This is something you will appreciate the difference between this direct energy deposition and the powder bed fusion process. Now that piece which you see, it is a metallic, it's a titanium alloy, titanium 6 aluminum 4 vanadium alloy. Now when the part with the geometry which is specified there on the figure, the total height is around 45 millimeters. It's a nozzle, and the thickness is 3 millimeters with an outer diameter 15 millimeter at the top, but at the base regions, the outer diameter is 20 millimeters. And in the central region, it is around 9 millimeters of the outer diameter. Now this part, this geometry, when it was produced by the direct energy deposition method, the total build time was 20 minutes. The same thing when it was prepared by the powder bed fusion technique, the total build time was almost 4 hours. Okay, so that somewhere highlights one of the lacuna with the powder bed fusion process. The build-up time is high, and this build-up time is high not because of the quality of the laser or anything to do with that, because if you look at the time that the laser scans on the surface, it's almost the same for both the processes. But the huge difference in the time, the build time in the direct energy deposition and the powder bed fusion process, it is because in all these powder bed fusion process, there is a step of recoating. One layer has been formed, the next powder layer is introduced, it is recoated. So that recoating step is something that is time consuming. And in fact, that recoating step is something that increases the total build time of the powder bed fusion process. Okay, so that is I hope I have the last few slides which I have been talking about has helped you all build in some more information about metal additive manufacturing processes. So now typically with this metal printing, there are certain issues with metal, because and these issues are particularly because that system that is being 3D printed, it is metal. Typically, if you understand in all these powder bed fusion processes, you would have noticed the similarity between the powder bed fusion processes and the domain of powder metallurgy. The porosity is something which cannot be avoided. So is it desirable to have porosity? Not really. Yeah, there could be some specific applications where we want a substrate or a material created which has got pores. But then normally we would not desire to have these pores, because what happens with the pores is that, if the pores are present, the overall density of the material is going to decrease, and that somewhere is going to affect the strength of the material as well. So porosity is a kind of a defect which is commonly, it's many a time seen during metal 3D printing, and low density again associated with the presence of porosity. There are, because of the changes in the temperature that happens during the powder bed fusion processes, particularly, even the direct energy deposition process, all of you would have understood there is a high, I mean, that the part is at a high temperature at some point of time and then it cools down. No? So that there are thermal temperature changes, thermal gradients established, which have a potential to create residual stresses, and it is normally seen. Okay. Now, once residual stresses have been built up, or certain the design of that component could be such that it could lead to the cracking of the part. So these are some of the typical, another reason for the crack formation in the metal printed parts, it is the local development of high stresses. Okay. So apart from that, the surface roughness, post-processing is mostly required. So during that processing, also at times it may happen that the surface roughness is, some finishing operation is being done. So that can also lead to the formation, I mean, that would add up to the surface roughness which is created. So those are typically the defects encountered during the metal 3D printing. And we could ensure that these defects are minimized by ensuring that the process parameters, the printer parameters are kept at the optimum levels. But before we talk about the printer, we need to understand our material system. That means the powder characteristic. Are they good enough? Have you got it from a good supplier or not? I mean, whatever properties, particle size, is it a size which is suitable for that machine or not? So some more remedies with respect to overcoming those defects. If one finds that the porosity is there and it is somehow not possible to eliminate them completely, then there is an option which may not be helpful every time, but there is an option, something like infiltration. Okay, in powder metallurgy also probably you would have heard about something like oil impregnated bearings. So there it is oil impregnation. So you could have an infiltration with a low melting metal or oils to ensure that the porosity remains at the lowest levels. The material parameters, particle size, shape, distribution, and the flowability, you should ensure that it is up to the mark. Typically, we would prefer to have rounded, spherical particles in order to achieve the best or the highest strength possible from that metallic system. Okay, and when we consider the quality of the metal powder, in 3D printing, it says that first and foremost, check the quality of the metal powders. In fact, these metal powders, okay, it's one of the reasons for making the entire 3D printing of metallic systems very expensive. The printers itself are expensive, definitely, but to add to that, a good quality metal powders, they are pretty much expensive. To ensure that the residual stresses are eliminated, it's essential that you have adequate, heat input provided. At times, it helps to preheat the sample so that the thermal gradients are not established. Okay, so thermal post-processing is something that can also help in some way to reduce the surface, to reduce the thermal stresses. And, see, it actually comes down to, once we have to, we really have to figure out what has caused the defect in order to come to, in order to be able to specifically talk about the remedy. But here what I have listed out, these are just generalized remedies to overcome or to ensure that minimum defects prevail in the metal, 3D printed metal sample. So to summarize now, this metal additive manufacturing, the advantages and the challenges associated with it, we all have seen that additive manufacturing comes with the big benefit of design freedom. Okay, so AM can make essentially any geometry with no restrictions, no tooling requirement. Material save is, losses are minimized. Material losses. This material loss minimization is particularly important in the aerospace industries where they make use of expensive powders like nickel and titanium and aluminum alloys also. Now those powders, the more your amount, you can reduce the wastage of those powders, you can reap benefits of it. Then some of the challenges with respect to the surface finish, yes, post-processing is something that is required to ensure that the finish is good enough. And at the same time, when we talk about surface finish, in fact, it is the layer thickness, which, if I decide to create thick layers and thin layers, that also will give a different kind of a surface finish to the part. Build rates are slower for high volume manufacturing. The printer cost is high. I just mentioned about it. Metal printers, very high. The cost is huge. And then there are also restrictions in terms of the size and also in terms of what material can be 3D printed. If you have a 3D printer, metal 3D printer, which you have procured to 3D print a particular kind of a system, you cannot use it for another kind of a material system, another metallic systems. Now, I could see someone had asked a question about what points to consider when buying a machine. So main considerations when you have to buy a 3D printer, when you have an option to buy a 3D printer, the speed of the printer, the cost of the product that you are able to create, the cost of the product, again, the cost and what all range of materials as well as color capabilities it will be able to cater. See, as per this Wohler's report, in the next 10 years, there is going to be a huge rise in the number of metal 3D printers. Okay. So there I have some more projections taken from the Wohler's report. And some, okay. I have, okay, my time. Can I take another 5 minutes and then I'll wind up? I've already.
Yes, and you can take 5 minutes.
Yeah. Because this was a very interesting case study, so I thought I should talk about it before I wind up. Okay, this is a case study from Bell Helicopters. Okay, so they needed components for their helicopter, and components they needed it on an urgent basis, certain components, and they wanted to set up a process to make those components again and again. So what they know, the entire purpose was to save time and money by eliminating the additional assembly which is required. So the main component which was identified for this particular case study was the ducting parts that the helicopter has for its ECS system. ECS is the environmental control system, which is there, which is a part of the helicopter. Okay. So the solution was offered by Stratasys. Okay. The problem was, the problem statement was from Bell Helicopter. The solution was provided by Stratasys in the way of laser sintering technology. Now, we have seen a lot about the laser sintering technology, so I am not going to talk about that, but I'll just say Stratasys direct manufacturing maintains stringent process controls and procedures to maintain the laser sintering machines and reliably deliver the reiterative pieces. Now that's the that's the design which they created. Okay, the design. Okay, the design was, this was for one of the part. That was on the right hand side. You see a picture of the defog duct nozzle. Okay. Now this is the design of the duct nozzle that was created, and that's the final part which you see there. Yeah, apart from that, other parts were also prepared by this Stratasys to address the issues faced by the Bell Helicopter company, and this is what I wanted to focus on. With these changes which they brought in by way of introducing those 3D printed parts, you can see those 4 ducting parts, and there's another defog duct nozzle. All these are the part of the ECS system of the helicopter. The weight savings that was achieved was 13%. The lead time reduced by 75%. Okay, so time saving is money saving. So lead time decreased by 75%. That is, using that particular design consolidation, it also reduced the number of parts. Okay, and in fact, these are all the advantages of additive manufacturing. If suppose you have an assembly created with 3 or 4 or 6 subparts, okay, you have the ability, the 3D printing technologies offer you the ability to create all those 3-4 separate parts in one go as one unit. Okay. So this Bell helicopter, they estimated a cost avoidance of $120,000. That was the cost saving because of the elimination of the conventional tooling and the rework. So overall, for this, but it's the same case study that we are referring to in the last statement. There was a 24% part count reduction. Okay, the number of parts which could be reduced by moving on to the laser sintering approach in order to replace some of those ducting parts. There was 24% part count reduction when the designs were converted to laser sintering, with 6 materials reduced and rework eliminated. The most crucial savings for this particular program was in terms of the weight, which is very important when it comes to an application like the aerospace, aviation, and even automobiles. So on that, with that particular case study, I would want to end this session, and thank you all for a patient hearing. And I am open for questions now.
We can take 2 quick questions and then we can conclude the session.
Sir,
yes, madam, I have one question.
Yes, sir.
Madam, you were talking about a powder bed fusion and 4 processes were listed under that title. Yeah. So can you please tell me that which process will be appropriate for medical implant out of that group?
Medical implant, sir, I'll tell you one thing. Without being specific about the material system, no, which material system would you want to work on? My question would be that one. What is your material?
Like say for medical implant, normally titanium is the preferred choice. So if you want to go with that material, then which process will be appropriate for out of that group?
The direct, see, sir, you saw that the lens process, in fact, anyone can be used, but it all depends on like, do you have that technology or not? That was one. Do you have that printer or not? That's again one thing to be answered. Okay, because these, if you have titanium powders available, in fact, all those 4, anyone you can use. SLM is very fine because it will ensure melting, and also that the part, you can ensure that the sintering is perfectly achieved.
Because some of the drawbacks were also identified with that group of process, density,
so that
etc.
every process will have something or the other, but there is a way to deal with that.
Yeah. Okay. Thank you, ma'am.
Sir, someone asked me about that SLS machines.
Yeah. Yes, ma'am. Myself.
Ganesh. So, are you a faculty or a scholar, research scholar?
I'm Professor Ganesh Borikar, faculty at MIT World Peace University, Pune.
Okay. There is, I think there's some. I'll probably you can take my contact details also. My email ID, I had shown it earlier. I'll give you again. And
yeah, definitely, ma'am.
What I remember, I mean, there was one company which I somehow have not been able to get, but there are something like Sculptech and Metamorph also, who are into this 3D printing of metals. And all these are, I mean, there are many based in and around Pune, actually speaking. There are some in Mumbai also, Mumbai Andheri side, but Pune has got many more because, you know, the entire, outskirts of Pune, you have lots of companies making powders, metal powders.
Yeah, I was basically interested in taking the input where the user's feedback is there.
Okay. In that sense, at least Mike, I mean, we don't have, I mean, I have not worked with any of these, we don't have any of those SLS or SLM machines. They are huge. I mean, they are very costly, expensive actually.
Yes, ma'am. Yeah. Yes, it's fine, ma'am. Fine.
There are many questions which are coming, but due to lack of time, we are not able to take it. So I thank Dr. Divya for giving a very beautiful talk with all the basics information, and even she add what are the defects are there in the metal and how to overcome it. So I once again Dr. Diva for taking this
My
wonderful
pleasure.
session. Thank you.
My pleasure.
Thank you.
Sir. Okay, sir, my contact number, I can give it to you if anyone wants to contact or something. No?
Madam, if anyone wanted to contact Professor Divya, just email me. Okay.
Yeah.
And
Okay. Okay. You can
I will
provide.
give
Yes.
you email ID, ma'am. No issues.
Yeah. Yeah. Okay.
No
Okay.
issues. Okay. We will join once again at 2 o'clock for another session. Thank you, everyone.
Thank you.
Yeah, thank you, ma'am.
Bye.
Okay, I think Dr. Vijay, have you joined? I have seen Dr. Vijay.
Hello?
Yes, sir, I can hear you.
Yeah, thanks.
So I am making you a co-host, sir.
Okay, fine.
Can you see now you are a co-host?
Yes.
Okay, okay, sir. Okay. So, yes, sir. Yes, sir. Now, fine, fine, fine. So what I will do is I will introduce you first.
Okay.
So good afternoon, everyone. I welcome all the participants for this session, and I welcome Dr. Vijay Hivarkar for this session. Dr. Vijay Hivarkar did his PhD from IIT Bombay, and of course we worked in the uh, same lab for some duration because uh, some of the work related to texture I did with him, and so I know him pretty well. And he has published in his PhD more than 10 publications. So his area of expertise is related with material characterization and that to texture. And after his PhD, he joined, I think, one of the company, I think I forgot the company name, where he published many patents. And thereafter, he joined Defense Institute of Advanced Technology, DIIT Pune, which is a deemed university funded by DRDO. And after that, he has developed many facilities in that Pune. I have personally seen those facilities. He developed a very good lab, and he's guiding PhD student and publish good impact factor publications I see coming out of it. So with this brief introduction, I hand over the session to Dr. Vijay.
Thanks, Dr. Pankaj. It's a nice introduction. And I would love to give some of my knowledge to the participants. Here, things are, see, as you said that 1 hour 50 minutes, I really need to find out that it will go into 1 hour 50 minutes or not, but I will try to cover it in 1 hour 50 minutes. Okay. I'm sharing the screen now. Is it okay, Pankaj? Dr. Pankaj? I'm sharing.
Wait, it will take little time.
Huh?
It will take some time. You start sharing it, it will take some time.
Okay.
Yes, now we can see it. Sir, make it full screen. I think then we can see.
Okay, fine. Let me do that. Now?
Yes, now it's visible, sir.
Okay, that's good. So can I start? Participants?
Yes, sir, you can start.
Okay, thank you. So good afternoon. As Dr. Pankaj has already introduced me, so no need of further introduction, but just brief additions about my institute. I would like to say something. I'm Dr. Vijay Hivarkar. I joined DIIT, that is Defense Institute of Advanced Technology, in 2014 in the Department of Materials Engineering. Then modified the department name is Metallurgical and Materials Engineering Department. After that, I switch over the areas which are more towards additive manufacturing, friction stir processing, and there are various technologies which are for the defense purposes where I am working. So DIIT is one of the premium institute in the
in India, and I would rather say that it's one of the defense institute in India. If you look at the worldwide, very few defense institutes are there. Out of that, one is in India. You can find out one in Cranfield also, but this is one of its own kind. And for TRI services, this is being utilized by the TRI services, defense R&D, public sector units, and some of the civilian candidates also can admit here. Here in DIIT, we have only MTech and PhD. We are taking the MTech and PhD through GATE, through the different interview processes. For sponsored candidate, we are going with the different way, and for the civilians candidate, we are going in a different way. So civilians candidate, we can admit through the GATE only. So this is a little bit brief about my institute, and there are various courses related to defense technology, like even the mechanical, but the broad area which we are normally covering is mechanical engineering, materials engineering, computer, electronics, physics, chemistry. All these departments are very well established here. So this is some of the idea about the Defense Institute of Advanced Technology. So to start with my presentations, the topic, I was thinking about what is the topic that I should keep it. So as the workshop is mainly dealt with the additive manufacturing, and I am working on the metal additive manufacturing, and especially on metallurgical aspects. If you look at the metallurgy, somewhat that whatever the conventional way manufacturing, and after that the final product which you are making it, that final product should have a very good property. So this is the final product of the conventionally made manufacture. But when you are going for a metal additive manufacturing, you may not get the properties which is normally being required for your final product. And for that reason, it is very important to study the metallurgical aspects of metal additive manufacturing. Okay, so I think this is just an overview about what exactly we are supposed to understand, why we are dealing with the metallurgical aspect. And it is also very important that every process has the different way by which you can understand the metallurgy, like the processes, the cooling process, the heating process, the way it is being built. So all these processes are giving a different mechanical properties, different physical properties, different microstructural properties. Because of that also, it is important to understand the metallurgical aspects. Okay. Dr. Pankaj, hello.
Yes, sir. I'm not able to. Sir, you are on first slide or second slide?
I am on first slide only. I just wanted to know that the other participants are joining. Who is going to join them? Are you or me? They can automatically join.
Sir, undergraduate is not there. Research scholars are there. Faculty members are there.
I'm just asking that in the joining, they want to my permissions, or they can automatically join in this Zoom app.
No, sir. I am adding it. No problem, sir. Don't worry about that part.
No issues. Thank you. Thank you very much. So, how to go ahead with this particularly metal additive manufacturing that is related to metallurgical aspect? I have just gone through the roadmap, that how the roadmap is supposed to be. Before that, wanted to show that the roadmap, the classifications, the introductions. First, I will discuss about little bit the introduction, why we called it as a 3D manufacturing, or maybe what is the definition, and then what is the applications, any futuristic applications are there. Then we will see just quick look about the classification of additive manufacturing. What are the metals? Then after that we can use that. What are the metals or alloys that being used for the metal additive manufacturing? We can see that other materials also that can be utilized in the additive manufacturing process. Then my choice is the characterization techniques and then the case studies. Though I know that the characterization techniques is the next topic which will be going to cover by the Dr. Rajesh Khatirkar. This I have seen through the brochure, but definitely I'll cover a little bit, and then the brief explanations can be given by Dr. Rajesh Khatirkar. Then finally the case studies, which are very important, and this case studies deals with the this 316 stainless steel, then the Inconel 718, and the titanium based alloys. So the brief introduction. Additive manufacturing is normally, sometimes people used to say that it's additive fabrication, 3D printing, digital direct manufacturing, additive layer manufacturing, preform fabrications. These all names, but it comes in additive manufacturing techniques. Okay, so whatever the name is, that name goes in the additive manufacturing techniques or AM techniques. Okay. So, as per the definitions of ASTM F279-10, additive manufacturing is defined as the process of joining the materials to make the object from 3D model data, usually a layer upon layer, as it opposed to the subtractive manufacturing technology. Yes, you know that the subtractive manufacturing technology, you have to remove some of the material and make the product. But here you are adding the material and making the product. So the geometric model is made on the three-dimensional computer-aided design, that is a CAD, and then like the CAD which is being used, the CATIA, SolidWorks, or maybe PRO engineering software we can use to make this product, the geometric model. Brief applications, detailed applications can be given later, but the brief applications about this, like they are using in the automobile industries, defense industry, furniture, jewelry, medical field, and aerospace industry. So, so it covers almost many areas where the additive manufacturing can be done. So if you talk about the technique, that how it goes and what are the ways by which you make the sample. So it's more important, as I told you, that the digital model, you can make it with the help of computer-aided design, and then conversion of this digital model into .stl format. So this .stl format, once you have done it, load this .html format in the AM machine, and then slicing up this .stl model once into the layer. Once you have made this slicing, you can building up the model by layer technique. Once you have made the product, after that, whatever the extra things are there, though they are supposed to be sticky portions, or maybe some extra portion which are being sticked, or they have been joined by weld or some other way, so it can be removed. So this can be done very easily, and then the last process which is being required, sometimes it may or it may not be required. If it is a property dependent, or the properties is so important, then it might be required. That is called as a post processing. Okay, so this is the way by which the additive manufacturing technique works. So these are the application. I have taken it from the net. So just check it out through the net. You will get it, that what are the other products which can be made through additive manufacturing technique. That is fuel nozzle, satellite antenna, hydraulic wall block, prosthetic parts, water connector, automatic engine model. So these are the very important things, and can be made through additive manufacturing. The most important, which I probably feel that this has to be done through, and it can be utilized. So the engine parts of the aircraft and so, Whether it is possible or not, we have to see that, and whether that, but it can be made, but as far as the properties are concerned, it needs to be tested heavily. Once that is being done, it may be utilized for the flight purpose or the aerospace industries. So there are some of the figures or the pictures which are there, which talks about the AM manufactured TI6AL4V light well component. So this can be utilized, but the size and other things also is one of the important types. Size-wise also, we need to understand that how big it can be made. It's very important that if you make the product of that size, it's very good. If you are unable to make the product, can you make the partial size and then another second part of the size and then join it? That also one can be done. So how it can be done, that is also part of research. So we will talk on this sometimes later, but this is an important thing where people have done it, the prototypes of the 3D printed sample, and especially on the aerospace application. So apart from the 3D the applications, we must see the classifications, how the additive manufacturing processes are being classified. If you look at the classifications, that these classifications, there are 7 classifications normally being done, and these 7 classifications deals with almost it depends on the processes that this plastic, metal, ceramics, they are covering, and some of the processes only uses the metallic, some of the processes are using only the polymers, and some of the processes are the ceramics. So the first process which talks about is, or maybe it's not a first or second, I'm just giving an example. The first one is from the website I'm talking about. The first process is the direct energy deposition process, that is called as a DAD process. This uses the thermal energy to fuse the material by melting, and this is nothing but a direct energy deposition method process. So the material is being used is in the form of powder or the wire in this process. If you look at the second from the left, that is the wet photopolymerization process. It's nothing but a liquid photopolymer resin or material being used, and this model is also constructed by layer technique. When it comes to the material jetting process, the material is jetted on the build platform using the continuous or drop on demand. Here the material being utilized is the photopolymers and the wax. The normal uses, or maybe the application point of view, is the investment costing patterns which can be made through this process. There might be some other applications, but this is what I have seen. So I have mentioned it, that investment costing patterns. So the binder jetting process is another process, that is a liquid bonding agent is selectively deposited to join the powder material. The powder-based material and the liquid binders are the material being used for the binder jetting process. Sheet lamination process. In the sheet lamination process, what we have seen that the sheet laminations are to be bounded together by ultrasonic welding. When it comes to the material extrusion process, material is selectively deposited, dispenses through a nozzle or the orifice, heated and deposited layer by layer, or the material is being used is the amorphous material. Now, the important technique which I am going further also, and most of the case studies are basically dealt with this only, and that is nothing but the powder bed fusion process. Here, the thermal energy is utilized for fuses the powder and the.
Dr. Vijay.
Yes.
Can you check your, I think, mic? Can you increase the volume? I think
Okay, fine. Let me see that. Hello? Now is it okay?
Now it's okay.
Okay, fine. So this is something related to the classifications of the additive manufacturing processes and how this classification is being given based on the ways and processes, how it is being converted in, and what are the materials being utilized. Based on that, only the classification is being governed. The technology-wise and the material being utilized for these technologies, this is the chart where shows that wet polymerization, the material jetting, the binder jetting, metal extrusion, and powder bed fusion. In that case, both the plastic can be utilized, but for the metals, only few processes can be adopted. That is that sheet lamination, binder jetting, that is a DED process, and powder bed fusion. Ceramics, there are only two processes, that is binder jetting and powder bed fusion. And the wax, which is the which can be considered as the material jetting process, only the wax is being utilized in the material jetting process. So importantly, whenever we are talking about the different additive manufacturing processes, we need to really understand whether the feedstock or maybe the material, what are the materials can be utilized, and what would be the initial material size, whether it can or the way it is going to be used, that is feedstock, and if it is in the form of wire or if it is in the form of powder. So based on that, only you can utilize the different processes. The similar way, that detailed understanding about the material being utilized, the polymers like ABS, PLA, PC, polyamide, nylon thread, the glass filled nylon, epoxy resin, wax, photopolymer resins. These are the materials being nowadays utilized for the additive manufacturers. For the ceramic purposes, that silica, glass, porcelain, silicon carbide being utilized. Metals, nowadays a vast applications, and it is also being utilized by small industries. The metals related and its alloys, they are now keeps on increasing their alloys, or maybe the different types of metals being utilized. So few of the metals I have listed out, like stainless steel, pure titanium, titanium alloys, Inconel 718, Inconel 625, then cobalt chrome alloy, maritime steel, titanium, as I told, that 15.5 PS stainless steel, the cobalt chrome having some different tensile strength, then aluminum alloy, which is ALS at NMG, or some other alloy elements also. If you add it, that ALS at 12 mg also it can be done, and gold, silver. These are the alloys which normally being utilized for additive manufacturing processes. So it's now I'm concentrating only on metals and alloys, and especially on 316L stainless steel, Inconel 718, and titanium alloy, that is Ti6Al4. In my future, whenever I'm going for a case study, I will be considering only these three alloys and go with this. So before that, we need to really understand what are the characterization techniques we can adopt to go for it, because it is very important that when I talk about the metallurgical aspect, one is to really understand that the metallurgical aspect, some kinds of properties and some types of characterization techniques needs to be utilized to understand the metallurgical properties, or you can probably say that the properties which are really important for product for the applications point of view. So the first property which is really important, that is in terms of mechanical properties, we can consider is here is a mechanical, or maybe sometimes it is being deferred in the mechanical properties, that is the hardness test. The hardness test is very important. We can go with the hardness as a bulk hardness, or you can go with the micro hardness test. The bulk hardness test, like Brinell, you can go with the Rockwell hardness test. So importantly, the idea is to you are supposed to get the bulk number, that is hardness number, and you are supposed to get the micro hardness number based on the where exactly you want to take the indent. So based on that, one has to decide that which one you want to go, and understands the whether viscous hardness or micro hardness test is feasible to you, or the bulk hardness test. Again, it's important that the size of the material is also very good. If you are having enough size of the material, then you can go with the bulk hardness test. But if you don't have, then you can definitely sacrifice and go with the micro hardness test also. Some detailed understanding where the research is really involved, and you need to understand that if there is a two-phase material, individual phases also you can go with this micro hardness tester, and you can try to understand. For again, further detailed analysis or detailed understanding, you can go with the nano indentations also. Nano indentations also will help you to understand the what are the on the particular phases or particular things, matrix, what are the hardness properties, so that you can understand through that. So the hardness is one of the important testing method, which will give you an transparent idea about the mechanical property. Some of the important properties are the creep test. Like if you look at the creep test, that the primary creep, secondary creep, tertiary creep, this is very important, that one is to really understand the creep property, because at the high temperature this is really important, and for this additively manufacturing process, if you are going for a high temperature application, the creep properties are very important. And we can go with the also the impact test. The impact test definitely ISOT impact test, you can go ahead, and with respect to the notch angle, depth and size, it is given here, and you can definitely go with the impact property, and you will get to understand that what is the impact property of your material. So these are the few things which are really important for specific applications. Here, the tensile testing, fatigue testing, these two testings are also very important when you are going for a cyclic loading. The fatigue testing is important. Sometimes of rotating bending moments also you can go with this and to try to understand the fatigue testing. So RBF is also, you can rotating bending fatigue also, you can check it out. The tensile testings also, you can get the stress test for elastic deformation, plastic deformation, yield point, Young's modulus, UTAs, proportional unit. Most of the things you will get through the tensile testing, and this is the important thing, that any designer would like to go with this particular property, like what is the bias of the material, and based on that only one can design the product. Because it is important that if you don't have the bias, the load appearing on the product and the material property, if it is not bias is not, then the product may fail. So for that reason, it is important to really go with the property which you are having, and the material properties is very important. So tensile property is one of this which needs to understand through this. Now comes to the material characterization techniques. The first important technique for that material characterizations includes microstructural analysis. There are various ways by which you can understand the microstructures, like start from the macro level to the micro level or to the nano level size. The optical microscopy gives you a detailed understanding about the micro level. That micro level, you can try to understand that what are the phases, what is the grain boundary, where the grain boundary is occurring, how the microstructure appears, what is how the grains morphology are taking place, whether the sample is having some cracks or not, or fracture is there or not. You can definitely see under the microscope through the optical microscopy. There are various different types of microscopes are there, like inverted microscope, the compound microscope. And these microscopes are helping to understand these kind of things. Application point of view, definitely you can use it into for life sciences, biological application, medical sciences, and most importantly, you can use in metallurgy. So this is just for an example. I just show you that optical microscope laser beam melted built aluminum alloy. You can see here that SiC and L4, SiC4, the precipitate which have been found based on the morphology, how this morphology we can able to detect the precipitates which are present in the material. Second is the most important thing for the metallurgists is the scanning electron microscopy. The scanning electron microscopy deals with a lot of detectors, or you can see that there are a lot of detectors like backscattered, the secondary. You can see the APSD also. You can see the force-scattered detectors, and EDX also you can utilize. So these are the detectors which are there, which will help you to understand the microstructure in detail and try to see that how you can be able to analyze this microstructure with the different modes. So this is one of the important techniques, that is scanning electron microscopy. The purpose is to understand the surface fractures, informations. You can get it. You can examine the surface contaminations, reveal the spatial variation in the chemical compositions, provide the qualitative chemical analysis by the EDX and so, and identify the crystallite structures also. The applications, life sciences, biological, medical, forensic sciences, and metallurgy. For the metallurgy is very important tool. The FACM, you can see the FACM of the LPM build. FE is FACM, that is field emission gun, scanning electron microscopy. Because of the resolutions, it is very important tool, that is field emission gun. And you can see here the microstructures wisely, and try to understand that what are how this morphology is taking place for a powder. This is ACM image of aluminum alloy powder, where you can see the bigger spherical and as well as the smaller spherical powders. There is satellite powder forms are also there, and these are really helping to understand whether what kind of powders you can go in, and what would be the morphology, what is the morphology of the product or the powder which is having before using for the additive manufacturing process. The next is, though I'm keeping it X-ray diffraction for this, but it is a different technique. You can see through the X-ray. This is basically the principle is a Bragg's law. You can use it, with the help of the Bragg's law, you can identify the phase determination, lattice, plane, determination of the residual stresses. So the important thing is that the X-ray will utilize for phase identifications, lattice plane determinations, residual stresses, and lattice parameter find out. And the crystallinity also you can understand with the help of the X-ray diffractions. So it is an important tool again, which will help to understand the phases, the residual stress, even the bulk texture and analysis also you can do with the help of the X-ray diffraction technique. There you have a texture goniometer where you can fix the texture goniometer in the X-ray machines, and then with that you can go with the measurement of the bulk texture measurement. So next is the transmission electron microscopy. In the transmission electron microscopy, the understanding about the transmission electron microscopy is utilized for various purposes, but for deep analysis, or whether you are really going for high-end analysis, you can go with the transmission electron microscopy. The purpose is the phase deformation is very, very important. The imaging modes are diffraction, that is bright field, dark field. Resolutions, it can go up to the 2 angstrom, and magnifications, you can see that there are number of zeros. The application point of view, the compositional study, crystalline structures, the stresses, the internal fracture, the contaminations, you can definitely see with the help of the transmission electron microscopy. Next is the microstructural analysis. The important tool in the SEM FITET, or maybe sometimes you can take it with the TM also, but in the SEM, what we can see particularly the orientation imaging microscopy is that if you can go with these tools, you can able to identify, understand the orientations of each grain. You can understand the phases which are present. You can understand the grain boundary characterization. You can do with the microtexture analysis. The different kind of study you can do. There are various tools which are available with this technique, and which will help you to understand the microstructures, the defects which are present, the types of phases which are present. You can go with understanding the stress strain analysis also sometimes. The individual local level understandings also you can do within the grains. Also you can understand whether any kind of misorientation is there, or any kind of strain is there within the material, or you can definitely understand with the help of the orientation is there. The orientation imaging microscopy, sometimes people used to say that EBSD, that is electron backscattered diffraction. So this is something which is really important for metallurgical aspects, where one can definitely see that what kind of phases are there, their properties related to materials. You can property in the sense microstructural property you can able to see. So this is a tool for the microstructural understanding. So apart from the mechanical microstructure, the physical properties also very, very important. So the density measurement, why I'm considering this part, because if you look at the additive manufacturing processes, you could able to find that the density is one of the important parameters where you may not get the density, which is a theoretical density in the particular processes. So for that reason, it is very much important to study the density also in that particular process. So you know that the density, by with the help of Archimedes principle, you can calculate the density, and that the mass of the samples weighted in air and the mass of the samples made in the water. Then through that you can calculate the absolute density, and with the help of theoretically density, you can calculate the relative density also. So these are the things which are in general people must have seen with the help of literature, or you can see that online internet that a lot of things are available. These are in general. But when we are talking about in details understanding about the 3D printed sample, and particularly in metallurgical aspects, one needs to really understand what metallurgical aspects one needs to see it, and how we can improve the properties which can be utilized for to compare with the conventional product, whether your conventional product and your additive manufacturing product both will go hand to hand, or it requires some kind of modifications in terms of property or not. For that reason, it is very important to understand the metallurgical aspects of the product and this additively manufactured product, and through that you can try to see how the post processing will help you for the product in order to get your desired properties, okay, which can be utilized for further applications. So in this particular presentation, I am just concentrating on the 3 important case studies. Other case studies also I have, but I feel that for this particular audience, these 3 case studies are very, very important, and I can go in details so that one could really able to understand that what are the important properties which can be understood through this, and with these processes, post-processing processes, how we can improve the properties in terms of mechanical property, or you can say in terms of microstructural understanding. So the first one which I'm going to talk about, that is the build on the AISI 316 alloy, which is nothing but the same, which is a austenitic stainless steel alloy, which is fabricated by selectively laser melting process. So here we have checked with the build orientation. If you see the building directions, how these building directions or build orientations will understand the property, or we can see that how the build directions will help you to get the property or differ the property in terms of direction wise. Okay, so this is very important. Second is in the same thing, post processing also very, very important, because you know that the processes which is being utilized, that is additive manufacturing process, this additive manufacturing process which really the solidification takes too much fast, so there will be chances of some changes in the microstructure which will differs the property. So it is very important to understand the post processing and or maybe the microstructure as built sample, and what kind of post processing needs to be adopted so that your property will be improved, and it will help you to put it in some of the product. Okay. So this just sorry. This is the first one. We will talk about this, and the second is we will talk on the post processing of Inconel 718 alloy, which is also fabricated by the SLM, that is selective laser melting process. Here Inconel 718, once it is getting built up, what are the post processing techniques can be adopted. Here also we can go in details. And third one which I have taken is that development sorry, I have not mentioned the title also. But the development of microstructure and wear properties by selectively laser melting process of titanium alloy. Here I am mentioning the titanium alloy, where if you add some more the particles, what will be the changes in terms of microstructure and other properties that we are going to study in this case. So I'm going here onwards one by one and in detail. The case study first. Hello, Pankaj. Dr. Pankaj.
Yes.
Can we take a break of 10 minutes and then we can
Yes. I think we can take a break of 10 minutes, and by that time we can solve little audio issue, sir. Okay.
Is there any audio issue still?
I will tell headphone you have, so you have to use headphone. I don't want to disturb. So by that 10 minutes we can see it, sir. Okay.
Okay.
So we can take a break of 10 minutes and then we can again restart, because I think Dr. Vijay is going to discuss the case study, and that is a crucial part.
Yeah.
Okay. Thank you.
Yeah.
Okay. We'll meet in 10 minutes. Okay.
Hello? Hello? Yeah. Am I audible?
Okay, we can start. Yes, yes, yes.
Okay, fine.
We can start.
So the case study, the first case study, I would like to give on the build orientation and post processing of a AI SI 316LR, which is again one can say that it is austenitic stainless steel, and when it is fabricated by the SLM process, what are the changes that are being observed in the SLM process that we will see. Sorry. Most important, whenever you are going for any kind of powder bed fusion process or any other process, it's important to see what are the powders which you are using, what kind of powder it is being there, what is the size, what is the chemical composition. So these are important things one needs to really understand. Based on that understanding, you can go further. So for this particular case, we have done some kind of ACM, which will try to understand that how these particles are being distributed, or what is the particle size for that particular batch. If that is the case, whether that particles are spherical or any other shape. If that is, if the particles are spherical, no issues, it will be utilized very well. If it is of different shape, there is a chances of that the product will also get deteriorated. Or maybe, I'm not talking about deteriorations, but there will be a change in the product quality. So the important thing is mostly that you can see, you can understand with the ACM, the size, the what is the distributions, the how this, whether it is spherical or any other shape, the morphology, and you can also see the chemical compositions at different locations. So you can try to understand that what is the chemical composition of that particular powder. You can easily see that. So this is the entire idea about the why we are considering the powder and why we want to go with the powder characterization. If you are getting some different kind of powder, like instead of spherical, some other shapes you are getting, then straight away you can say that I don't need this kind of powder. You can replace the powder, and then further you can go ahead. So like that, if chemical composition is something different, so you can definitely ask to the vendor that the chemical composition is changed. So instead of going for a final SLM process or any additive manufacturing process, you can definitely try to see this kind of aspects. This is after product, the powder and making up that how this product is being made. And after making up this product, we have just shown you that after making the product, how this it is appearing. We have given for particular SLM process some the parameters which are very, very important. These are laser thickness, which is normally coming around 30 micron, 30 to 35 microns, but exactly in this case is 30 micron. The platform temperature box around 80 degrees Celsius, hatch angle which is 67 degrees, the laser spot diameter is almost 100 micrometer, laser scanning speed, the 1000 mm per second, recruiter speed 80 mm per second, oxygen concentration is also 0.1, overlapping ratio is 10%, and some other parameters are mentioned here. So these parameters, if you have the some other the packages where you can change the parameters, you can definitely change the parameters and build your product accordingly with that parameters. But if you don't have the packages along with the machines, you cannot change, or any customized machine is there, then and then you can change the parameters for making the product. Okay, for particular material or particular alloy, the parameters are fixed, given by the vendor, the machine manufacturer, and the set parameters you have to use for making the product. So the chemical compositions, we have again checked it for a powder and try to understand that what are the percentage of Fe, chromium, nickel, or alloy elements are there, Based on that, whether go, no go can be done. Once you have made the product, it is essential to see whether what is the density. So density is somewhat, you can check it, as I already shown in the earlier slides, that density can be measured with the help of Archimedes principle, and you are getting the relative density. The density here, if you look at with the directionality, build directions, if you look at the build directions or orientations, at 0, you are able to get a very good density, and later for 45 degree or for 90 degree to that build directions, you are getting the density is little bit comes down. So the actual density which you are supposed to get, that you are not getting, or maybe you can say that the theoretical density is not achieved with the help of this particular parameters and the processes what we are doing. So what are the, where is the remaining density? That remaining density you are getting in terms of porosity, like porosity or some other defects. Like here we have checked the porosity with the help of optical microscopy, and we are seeing some kind of porosity here, and these porosities are in microns. So you can see that the micron porosity with the help of the optical microscopy, and try to understand that why this density is come down. So this SLM process along with the standard parameters, sometimes you won't get the desired density what we are supposed to get. If you look at the optical microscope, optical microscopy of the, or you can say that the images you can able to see with the help of the optical microscopy, what you are seeing that you can see the laser marks, you can see the hash angle for all three things, longitudinal, front, and perpendicular to the BD directions. You could able to see the longitudinal sections, what we are able to see here in the different sections actually. Then the front section you could able to see, and in perpendicular to BD also you can see. So in all the sections, trying to understand that any morphology or any changes, we could able to see and try to understand why these changes are occurring. So these are the things which really important, by which you can able to see that microstructure, what is the hash angle, where is the laser mass you are able to see or not. So that things you can able to see with the help of the optical microscopy. This is one of the technique where you can see if you go in deep analysis and try to see that within the grain, what is the structure that is occurring, and you can see there's some kind of cellular structure is there. This is the cellular structure which is seen in terms of SLM process. That you can see that EQX type of cellular structures, or you can say that the cellular structure which are coming here, these cellular structures are getting within the grains. You can able to see with the help of the EBSD also. We have taken the image quality map and the overlap the IPF map, that is inverse pole figure map, and EBSD map, and trying to understand that whether there are different some kind of variation in the grains, or maybe there will be any kind of misorientation that is there. We are not seeing that much variation in that particular cellular structure. So we have just check it out with the help of by putting the 2 points and drawing the line. With this help of, you can able to see that the point-to-point distance, there is not much change observed in terms of misorientation angle. We have taken the EBSD, and through the EBSD, what we could able to see that with the different sections, if you look at the building direction and 45 to the building direction, the kind of colors which you are seeing why I'm saying the colors, because it might be the audience is different. So I just wanted to just keep it to that level. Otherwise, the orientations are related to that colors, and this indicates that 101 and 111. If you look at the IPF triangle, you can able to see that 001, 101, and 111 things are there. That is IPF map, and this IPF map will give you a real understanding about where the grains are oriented. XRD also we have done with the help of that particular 0 and 45-degree orientations, and what we have seen that the peaks which are getting in this case, the peaks are also of the similar type. There is no other extra peaks which you are getting. The peaks almost are similar. If you look at the tensile that for the horizontal, inclined, and vertical sample, you are seeing that the YS for horizontal, inclined, and vertical sample, there is a little variation. That variations is you could able to see that vertically it is down, and when it comes to the horizontal, it is horizontal and inclined, it is almost same. But when you are talking about the 0 degree, that is that comes 680 some MPa, and when we are talking about the inclined and the vertical, it has again come down. So with the help of the building directions, the properties is changing. That's what here we need to tell you that there is a change in property when we are going for the building directions. And here the building directions, when you are going for a vertical direction, which is the perpendicular to the building directions, that is 90 degree. So what we are seeing that the changes which are being observed, and they are with respect to YS, UTS, and elongation, you can able to see. The residual stresses also you can able to see. The idea of doing the residual stresses that once you are done the as-built samples, we have to go, as I told you, that post-processing effect also one is to really understand, and this post-processing is being done with some temperature, that is stress relieving, and heat treatment also we have done at a higher temperature. What we have observed that whatever the compressive stresses there, these compressive stresses which are appeared or occurred due to the selective laser melting process, they are coming down with the stress relieving or the heat treatment operations, and you can very well able to see with the help of the residual stresses. If you look at the conventional way made samples and the selectively laser melted built samples, what we are seeing that the stress strain curve is clearly showing that as-built sample having better elongation as compared to the as-built 90 samples will give you a better elongation as compared to as-built 0 and as-built 45. So this 0, 45, 90 is just conventions which we have given, but actually the building direction is parallel to building directions, inclined to the building direction, and perpendicular building direction. That is a nomenclature in the real sense. In a conventional way, what we have taken from the literature, and the values are much better than as compared to conventional way. But we need to really address this thing in terms of different conventionally processed samples. This is one of the conventionally processed samples, and we have checked with this conventionally processed sample with the as-built sample. So this as-built sample gives you much better things. But if you go with the post-processing, like stress relieving operation, you can say, or you can say the heat treatment operations, little higher temperature, you will able to see that the residual stresses are decreasing down. So the stresses which are there, which is a compressive residual stresses, that can be minimized. So these are important post-processing treatments which you can do on the as-built sample, particularly an 316L alloy. This is the same one, the effects of stress relieving. I'm sorry, I'm just taking it this side. Effect of stress relieving and heat treatment on tensile and impacted properties. You can see that the Charpy impact test, the properties, you can see here the as-built for 0 and 45, 45 is much better as compared to as-built 0 orientation. So in all the cases for stress relief and heat treated, it is showing the best better in terms of 45 orientations. So the impact energy which we are able to see here is in terms of difference, we can see the as-built to 0 orientations and 45-degree orientations. There is a difference you can see, but if you are looking the difference in terms of as-built to stress relieving and as-built to ST, that is heat treated, you are seeing that much difference, and that difference is in terms of that half of the properties, that is impact energy you are getting. So this is very important that what happens to due to the stress relieving and heat treatment, that so which post-processing treatment needs to be adopted while going for the operations. That is important. So there is some kind of trade-off, whether SR is okay, so that you can minimize the stress, you can minimize the stresses which are present in the after the building, or there are heat treatment. So depend on what kind of applications you are using it. Based on that, you can choose the stress relieving operations or the heat treatment operations, which is nothing but the handling operation. So you can see here also is a two-stage two-stream diagram. In that also you can see that as-built 0, SR and ST 0, there is a difference in terms of YS. Similarly for 45 also, as-built stress relieving and heat treated, there is a difference in terms of 45-degree angle. There is a difference. So that difference you can very well see with the help of stress strain curve. One more important post-processing treatment you can do it, that is hot isostatic pressing. So what hot isostatic pressing does, that it tries to minimize the porosity or try to improve the density of these samples. Once it is being improved, what are the changes that have been occurred in terms of tensile and impact property we have measured. So what we have seen that the as-built samples which we are able to see that the YS is much better, but due to heat, because it's again the temperature is involved. So you can see that there is a drop in terms of YS. But if you look at the definitely the elongations and the UTS, they are somewhat matching. So this HRP will give you better somewhat matching UTS, but there is a chance that the drop in the YS. So impact energy also, you can see that impact energy which you can achieve with when we are talking about the as-built sample, whatever the as-built condition samples are there, that as-built condition sample, the impact energy was there. So the similar kind of impact energy that you are getting after hot isostatic pressing. So this is all together trying to understand that whether these particular processes, which are nothing but the processes, whether they are important to get the desired properties or not. Because sometimes the as-built conditions, you are getting a lot of stresses, as you have seen here, that compressive stresses are there. These compressive residual stresses, which will create the which may create the problem during the loading conditions, or maybe when they are in the operations. So whether that has to be relieved, the stresses has to be relieved completely, or what processes can be adopted, that can be done with the help of the post-processing and try to gain some kind of properties or try to reduce some kind of properties. So it's a trade-off kind of thing here, which post-processing techniques you need to adopt and what property you need to gain and what property, if it is minimized also, it is okay for you. So like that you can see the post-processing techniques. So the second case study, which is very, very important, that is on Inconel 799. This particular material is normally being utilized for the aerospace industry also, particularly for the jet engines and so. The engine material is, we can say, the engine material for the aerospace application. And if you look at after making the product, what will happen to the by the additive manufacturing process, what is the property in terms of mechanical or in terms of microstructure. So we will go here one by one and try to understand. First, we are looking at what are the phases that were present. And once we have seen that the phases where they are intact as built conditions and in the STA, that is the as-built condition is nothing but we are saying that after making a sample, what is the XRD pattern, and then after that the solution treatment annealing. What is the XRD pattern? Then after that, hot isostatic pressing and double edging. What is the pattern that we are getting? Here we can able to understand from this XRD plot. The microstructural characterizations, which are very, very important, and it has to understood, as I told you that in the first case study also, what is more important that if you are looking, going for any building product, initially you have to really do the powder study, and that powder study can be done with the help of ACM. As I told you in the previous case study, the similar way we can go ahead with this and try to understand. We have made some samples that is in terms of the rods and try to see that the powder form, what is the chemical compositions, particularly at the spectrum 1 and spectrum 2 with the help of IDAX. With the help of XRD also, as I have shown earlier also in the similar way here also, the peaks where they are forming and what are the compositions of that thing we can able to see from this slide. So it's more important that microstructure. Once you get the microstructure, what you need to see? You can see the medical boundaries, you can see the laser scan path, you can see the matrix and the phases which are present, and you can see the what are the chemical compositions which are present in the material. So here, the first we can see here the melt pool boundaries. You can see the curvatures are there. Here, the laser scan path also you can able to see, and then later the phases, that is the matrix phase, and some other phase, matrix which is there, which is important, and the gamma phase here, and some kind of large phases also you can able to see here. What will be the change once you are going for solution treatment annealing? So solution treatment annealing, your microstructure is completely changing. You can see the dendritic structure again, but the structure may not be changed to that level. But yes, there is a slight change in the microstructure you can see. And earlier also, as I have not showed it here, but the microstructure after STA also you are getting a built also you are getting a similar kind of structure. Even after STA also you are getting a almost similar structure. So chemical compositions after aging, whether you can able to see some kind of phases are also there or not, you can able to see with the help of ACM and the EDAX. So once you are done with this STA, the same as-built sample or we have changed the sample. The as-built sample we have gone for the hot isostatic testing and hot isostatic facing plus double edging. What we have seen in the hot isostatic and double edging that some kind of twins are generated. We can able to see some phases are also being developed more in the number of ways, or you can say that more as far as the concentration of the phases is concerned, it is increased. And you can see the microstructure changes are also being observed. You have seen the dendritic structure in the earlier case, and later case you have seen the structure is going to be somewhat different as compared to the dendritic structure has gone out and the new structure has come in. So, and in that new structure, you can able to see the different precipitates. You can able to see the kind of screens which are there, and considering all these facts, how the structure is changing with the help of HIP and HIP plus double edging, that could be seen with the help of optical micrograph and the spectrum which is taken from the backscattered, which is used along with the SEM, we can able to see. The EBSD is one of the important tools by which you can see the orientation mapping. You can see that how the boundaries are being intact. You can see here some kind of density structure in the at-built conditions. The building direction is already shown here. And then in that this EBSD map also clearly shows that orientations, what kind of orientations are there in the material. So once that is done, what changes you could able to see after STA process also you can able to see. So not much changes, as I told you that not much changes you can able to see in the as-built and STA process. A similar kind of structure we are seeing. There is a little change in terms of when the boundaries like high angle and low angle boundaries, but low angle boundaries it is little bit reduced, but yes, this is also very important that the low angle boundary we are considering 0 to 5, and that 0 to 5 whether some kind of analysis needs to be done with the help of the EBSD tool, which is a software available. That is a TSL software in our lab available. We are done with this and trying to understand that any boundary changes are there, any kind of misorientation is there within the boundary or within the grains, we can able to see. When you talk about the HIP process and HIP plus double edging process, the HIP process will give you an idea that what is the densifications that is being occurred. Once that densification is done, so here we have got 100% densifications, and then what we are seeing that after getting that the microstructure study we have done, we have seen that there are some kind of twinning which we have done. The big grains are there, and some kind of precipitates also we have seen. To go with the double edging kind of things, the double edging will give you an idea about whether any precipitate further evolved or not, the tuning is being intact or not, that also we are able to see. So tuning was there, some kind of precipitates are further evolved during this double edging process, and which will give you impact in the properties. These are the ingrained misorientation maps, which will give you with the help of EBSD software. And this what it indicates that in the as-built conditions, this the misorientation is very high, the strain is there, and once after the as-built condition, if you go for the solution treatment annealing or HIP plus double edging, so all these things, what we are getting that misorientation is dropping, the ingrained misorientation is changing. This occurs in both the grain average misorientation, kernel average misorientation, and grain orientation. So this is ingrained misorientation mapping, and it is denoted by the different techniques like the GAM, that is the grain average misorientation, and the kernel average misorientation. That is, here GAM is nothing but gives you a better idea And in the same way, the kernel average misorientation also gives the better idea in terms of misorientations within the grains and so. If you look at the evolutions of mechanical property after all these processes, if you look at the first property, hardness, what we are seeing, the hardness is improving. Starting from the as-built to HIP plus TA, you have seen the hardness has improved drastically. This will help you. Why this is happening, as I told you that there are the precipitates which are forming, there are the twinnings which are generated, which will help you to improve the hardness. Double edging, which will also give you a better impact. There's some sort of precipitates is also evolved in the double edging process, and this will help you to get the better hardness. If we are talking about the relative density, as I told you that HIP will give you better density, and it is almost closing to the 100% that we are getting. In the similar way, what we are able to see that the engineering stresses, the similar way, the approach of getting this, if you look at normally what are casted Inconel 7-1 alloy and as built STA and HIP DA process, you are getting in this case the better product is after post processing, that is hot isostatic process and DA, you are getting the better properties in terms of if you look at in terms of UTS, in terms of YS, and in terms of elongations. Just wanted to give one tell you one announcement actually. Here the power has gone, so there will be chances that my monitor is getting off. Once the power is come, I will join. But here, till the power gets, I have this backup. So I will see that how we can go fast and try to finish it. Okay. So we will go with the third case study, that is development of microstructure and wear properties by the selective laser melting process. What we are seeing that we are used in the powder itself, the boron and sometimes the TIB. So the boron which is being utilized, these are also micro level and sometimes the nano level also we are used. With the increase in the boron percentage, the chances of the you can see the melt pool boundaries how it is going to change. With increase, they are much you can broader, and that broader in the sense that you can easily see this kind of melt pool boundaries. So this particular classifications, you can able to see that how this changes is being occurred when you are going with the different kinds of boron percentage. You are seeing that the first one you are getting the structure is completely magnesic structure. With the adding of this structure 0.1 to some 1.5% boron, you can able to see that the structure is changing, and you are getting the almost at 1.5 the equivalent structure, and you are seeing that the TIB which is the TIB2 which is being forming. So the TIB which is forming here are definitely concentrating with the percentage, and thank God the light has come. It's very good. So the percentage development in terms of the 1.5 boron, or you can say the 1.5 TIB. So what we are trying to say in this case that if you are adding the boron percent or if you are adding the TIB 2%, the ultimate outcome is what we are getting is the TIB concentration. So we can increase the TIB concentrations, and we can see that there are some viscous kind of morphology that are getting in terms of TIB. So the first, which is very important, that what was the Ti64 morphology, that is the martensitic structure. We keep on increasing the percentage of boron or percentage of TiB2. We are getting the morphology change. We are getting the TiB in this case, and the morphology of TiB is a viscous kind of thing. So elongated needle type of morphology that we are getting in terms of TiB. And we are getting the alpha phase also here, which is again an important phase for TiB structure. So the Ti6 alloy which we are seeing here is completely different with the additive manufacturing process. Ti64 in normal case, what we are seeing that there are two phases which are there, that is alpha phase and beta phase. In the additive manufacturing, particularly SLM process, we are not getting the beta phase, we are getting the martensitic structure. But with the modifications of by adding some kind of the particles, we can modify the structure. That's what I wanted to tell in this thing. Here, the image study also we are talking about that the Ti6Al, that needle shape you can able to see, and this needle shape, how it is going to be changed, you can able to see with the top images. The complete needle shape is going to convert into the equiax kind of structure after 1.5% of boron. Hardness and tribological behavior also we have understood, and trying to see that the hardness is increasing with increasing the boron concentration. You can definitely ask that initially there is a martensitic structure. That martensite, why in normal cases the martensite is the hard structure, then why it is not getting the better hardness as compared to? But as I told you that here the martensite which you are getting, that is a different martensite compared to what martensite is normally getting in the steel. So that's why there the hardness is basically the shearless. We can probably see that because of the carbon concentrations and the shearing which is being occurring, shearless diffusion, diffusionless shear transformation which is being taking place in this case, the case of the steel. Because of that only we are getting it. Here particularly the hardness which the martensite which you are getting here is completely different than what we are getting in the steel. So importantly, why this this structure is getting evolved and why this micro hardness is enhancing. The more important that with increase in the boron concentrations, you can see that the micro hardness is getting really increased. In terms of wear properties also, you can see that wear is also getting improved with the increase in the boron concentration. So which helps you to understand that we can add little bit the precipitate particles in this case and try to see that how the properties are going to be changed. This is the kind of study also one can do with the help of additive manufacturing processes. So the warm-up surface also we have tested. This is another study which we have seen that what are the changes that are occurring, where is the groove is splitting, where is the wear track, where is the debris. That also we can able to see for the as-built Ti6Al 4V and this as-built Ti6 with 1% boron concentration. So we can see that why these changes are occurred and why this wear properties are improved with the increase in the boron concentration. Once you have made the titanium alloy, that is Ti6Al 4V alloy with some boron concentrations, we have studied the annealing of this Ti6Al at 850 degrees for the 2 hours. What we have seen that the changes how the changes is taking place in terms of morphology, in terms of grain, in terms of microstructure we have seen. So Ti6Al4V microstructure, we have seen that how this after heat treatment there is a change. We can see that there is a beta phase also has been grown up, and for each and every concentrations of TiB2 or TiB, we are seeing that there is a change in microstructure, and that microstructure we have understood in a different way. So we have got due to annealing the second phase also, that is a beta phase, which was not present during the additive manufacturing of Ti6Al4V alloy. But after annealing, we have got the beta phase, which was absent in the earlier phase. So this is a phase graph which we have taken from the EBSD. What we have seen that the EBSD, the beta phase is very well evolved in all the cases. So the grain size distributions of the beta phase also we have seen, and that Ti6Al4V, we are getting the grain size of almost 1.2 micron. But as we are increasing the TiB2%, we have seen that with more TiB2, we are trying to reduce down the grain size of the beta phase. The GAM and the grain average misorientation also we have seen both for the alpha phase and the beta phase, and what we have seen that the changes which are there at 1.5U and the Ti6Al, there is a little change which we are able to see both in alpha phase and the beta phase. In terms of microhardness, yes, with the anneal sample from 340 to 397 HV, we can able to see the microhardness with additions of percentage TiB2. We have done some kind of wear test also. What we have seen that wear test for annealed sample. The annealed sample, if you see the trend at 1.5% TiB2, that the changes which are there, that changes the improvement in the wear performance you can able to see after annealing, and that improvement percentage increase in the TiB2 also improved. So this is also one of the important findings. So we have seen the ACM microdrop of worn out surfaces. What we have seen, some kind of detached particles, some kind of delaminations. So the idea of showing all these three case studies where we have talked about the 316L samples, we have spoken about the Inconel 718 alloy, we have talked about the titanium that is two-phase alloy, that is Ti6Al4V alloy, by addition of some of the particles, that is TiB2 and as well as the boron particles. What we are seeing that if you are making this product with the help of additive manufacturing processes, there will be the changes in terms of property wise, and that property wise you cannot match, or maybe you are unable to match with the existing parameters or whatever the parameters are being utilized with the how you are making the product with the conventional process. The product which you are making with the conventional process and product we are making with the additive manufacturing. Does it require the post-processing or not? So what kind of post-processing you can go ahead, and how the properties are changing, and what is if the properties are changing, what is happening in terms of microstructure so that the properties can be changed. So the structure property correlations also we can easily adopt with the help of these things. So this is all about the case studies, and thank you for your patience and hearing me nicely. Okay, thank you very much.
Thank you very much, Dr. Vijay, for your presentation on this metallurgical aspect of 3D printed metal parts. From audience side, any questions you can type so that Vijay can answer a couple of one?
Yes, I would love to answer it.
Yes, yes. We can take a couple of questions. Okay, sir. I have to ask some questions, sir.
Yes.
I think in the first this steel one, actually, sir, the HIP process and then AD one. Okay, can you throw some light so that audience can get some information?
HIP
Mechanical
and
property.
See, HIP is nothing but the hot isostatic pressing. It is normally there won't be any change in terms of the dimensions wise. Once you go for a HIP process, that is hot isostatic pressing process. If you go with this, at particular temperature for certain time, it is being done, and this will help you to minimize the porosity of the little defects which are present in the material, and this will also help you to improve some properties. I'm not talking about the YS or VPS as compared to the earlier, but it is very important to understand the physical properties, whether that porosity is reducing down, so definitely it will help you to get it better properties in terms of other aspects. That is stress relieving aspects also you can get it in the better form. But during in the operation conditions, you might see that there is a failure, and that failure could be due to stresses or due to the porosities which are present. That can be minimized with the help of this. But definitely it depends on the application, which applications one can use. Secondly, the second thing is that you are asking about the double aging process also. You can go with higher temperature, the aging one, and then keep the lower down the temperature, and then go for some time. This is double aging is particularly we are doing for the Inconel 718 alloy. The temperatures are little bit higher temperature for the first aging, and then after certain time you can reduce down the temperature and hold it that temperature for some certain time. So
Okay,
this
okay,
will help you to improve the precipities which are being there inside, and they are also helping to improve the mechanical properties, as
Okay,
you have
sir.
already seen in the PPT.
Vijay, actually, there are two more questions we can take.
Yeah.
First question, can you tell us more about GAM and CAM and what we can conclude from these studies?
Which one?
So can you see question in chat? You can click in the chat box. Question asked by Shantanu Devnath sir.
CAM and okay. Yeah. More about the CAM and what we can conclude from these studies. Yeah, it's a very good questions. I would love to answer with this because I want the audience to ask these questions, because these particular things are not regular practice. GAM is nothing but the grain average misorientation. This you are getting from the EBSD software. That is in our lab we have a TSL software. That is one of the EBSD software which will help you to get this GAM and GAM. GAM is nothing but the grain average misorientations that is occur within the grain, and CAM is also one of the grain average misorientations. So it's a point-to-point misorientations we can consider here, and CAM is you can consider the point and periphery around it. What is the misorientation between those 2 points? The surrounding one we are considering. That first periphery or second periphery, both the things can be considered as CAM. But the conclusion, what you are really asking me, that yes, if you keep on GAM, if the misorientation is more, you can relate that misorientation with the strain. Okay, what kind of strain that is being there in the material, or what kind of dislocations are there in the material, that relations you can get. This can be done both for CAM and GAM also. So this will help you understand the stresses which are present in the material, or any kind of stresses if it is there, it can, or within the grains if it is there or not. Yes.
Okay, then the last question we can take is even that is of interest to me.
Okay.
About this composite sample preparation. I think basically what Mr. Prashant is asking, before performing this additive manufacturing, how did you prepare the sample?
Okay, that's most important. Actually, it's one of the technology. See, you know that the milling, ball milling and something. But what we have done in this case that we have customized the thing, ball milling things, and we mix this and test the number of rotation after number of rotations. We have checked it down whether the powder is properly mixed or not. So you can probably say that customized ball milling operations where we are not going to deteriorate the powder, but we are trying to mix the powder. Okay, and then that mixing is supposed to be homogeneous. If it is being homogeneous, then further the powder can be utilized. Otherwise, well. So after mixing the powder, we have checked with the SEM and seen that the powder is homogeneously mixed.
Okay, okay.
I think
Sir,
answer
take
will be
last 30-second questions, Vijay.
Yeah.
What facilities are available at DIAT for as like SLS or SLM?
See, for metallurgical samples, we do not have the facility, but yes, we are using the DRDO facility and some of the industries facility which are available. But very soon we will try to procure it, but not in a year or two. But,
okay, okay.
Yeah,
okay.
in the Pune we have the facility available in other DRDO labs, which you are going to use it.
Okay, okay. Thank you, Dr. Vijay, for giving a lot of insight in this presentation, right from basics to actually the metallurgical aspects, and the faculty member and the research scholar who are gone through your presentation. They can understand at what level they have to work if they are picking up the problem related with 3D printing or additive manufacturing, and then try to get a patents and publications. So this is a very nice presentation, and I thank you for giving this wonderful presentation. Thank you.
Thanks, Dr. Pankaj. You have given me opportunity to speak something about the audience in front of audience. It's very helpful for me also, because brushing the things, though this work has been done little 1 or 2 years back, but brushing it once more is really important, and this platform really helped me to brush up the things. Thank you very much, and thanks to the audience for patiently hearing me.
Okay, okay. So we can take I think 5 to 7, 8 minutes break we can take, so that next presentation is by Dr. Rajesh Khatrigar. So we can take a 8 minutes break minimum.
So I'm leaving the.
Yes, Vijay, you can leave it. You can unshare the screen, sir. Okay.
So I have done it, I guess.
Okay, okay, okay.
Yeah.
Dr. Rajesh, are you here?
Yeah. Yes, Pankaj, I am there.
Okay, okay, okay.
You can hear me properly, right?
Yes, yes, yes. Now I think audience also, I think there will be no issue now. Can you type yes if someone is here? So Rajesh, I am making you a co-host.
Okay.
So that you can start, after 5 minutes, you can start sharing the screen.
Yeah, I have already shared it.
Okay, 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 okay.
So
okay, no issues.
Screen, right? Yeah.
Yes, yes, yes. Just make it full screen and then.
Yeah, I'll do that.
Okay.
Okay, just 1 second. So actually it's not becoming full screen.
Okay, okay, okay. No problem, no problem. I think I will just make it at my end full screen. I will make it. so that for audience it is visible in bigger.
Yeah, yeah. Yeah, now it is okay.
Okay. Okay. Okay. Fine.
We'll meet after 5 minutes then, okay?
Yes. We'll meet after 5 minutes.
Yeah, okay.
Dr. Rajesh, can we start?
Yeah, we can start. No issues.
Okay. I will introduce you first to
Yeah.
the audience. Okay. So good afternoon, everyone. I welcome you for this new session. This session will be conducted by Dr. Rajesh Khatrikar. So Dr. Rajesh finished his PhD from Metallurgical Engineering and Material Science Department from IIT Bombay, and it's my department. And he is currently the associate professor in Vishveshwaraya National Institute of Technology, Nagpur, and that is my hometown. And I remember Rajesh worked on the first machine which Professor Samazdar brought, and then later on second scanning electron microscope with EDS machine came, and he is the first student or first or second student of Professor Samazdar. Worked in the orientation area. I think he has put a lot of effort in building those facilities. And after a PhD, he did a lot of work. And you can visit his Google Scholar webpage and the amount of publication he did. And one of his publication is in Philosophical Magazine. With his one of the student, Dr. Amit Kumar. I know him well because he was my earlier colleague. So with this brief introduction, I welcome Dr. Rajesh Khatrikar, and I hand over session to Dr. Rajesh Khatrikar to continue.
Okay, thank you, Pankaj. Actually, as he already told you that he was my colleague during my PhD. So I thank him for giving me this opportunity to talk about characterization of materials in this particular course. So basically what I will be doing is that I will be going to give you a overview of characterization techniques which can be used for materials, different materials. Now here I have not distinguished between 3D printing and conventional materials. So whatever techniques we can use for conventional materials, same can be applied for 3D printed materials also. So it's a general, basically you can say, what I will be doing is that I will be giving you an overview of characterization of materials with what technique you can do what, okay, and what is going to be its utility, what are going to be its advantages and disadvantages. And then I will start with the very basic technique, which I think all of us know, optical microscopy. So the first thing which I will be telling you is about optical microscopy. So I'll be starting with optical microscopy, then slowly I will be moving to scanning electron microscopy. Then the third technique which I will be covering will be X-ray diffraction. And after that, if time permits, then maybe whatever Pankaj talked about, texture, orientation, crystallographic orientation. So just a glimpse of that, okay? Because in this particular 2 hours, it is going to be very difficult to cover all this technique. So what I will be doing is that I'll be just giving you a brief overview of all the characterization techniques. And I have made this presentation assuming that all of those who are attending are students. Okay, so it's a very basic presentation. Now, at any point of time, feel free to stop me and ask questions. So it can be online, like when I'm going on with the presentation, that time you can ask the questions, at the end you can ask. So whatever is your choice. Okay, and before that, I will just tell you what are my different research areas. So I work on deformation, recrystallization, recovery, and of course in all these things, texture will be involved and characterization will be involved. And since I'm in metallurgical and materials engineering, I will be deeply involved with the characterization of these particular materials. Okay. Next. So this is the outline of the presentation. So what I will be doing is that I will be giving you a brief introduction to materials characterization. What does it mean and what is its importance? Then I will be going to optical microscopy, scanning electron microscopy, X-ray diffraction, and some advanced microstructural characterization later on at the end. Okay, so this is the first slide which usually I put. So in introduction to materials characterization, so there are, whenever we take any material, there are a lot of questions like whatever may be the material, it may be a steel, it may be a polymer, it may be a ceramic. So there are basically a lot of things which you can do with that particular material. So in characterization, in materials characterizations, these are the questions which typically are important. Now, first of all, what does characterization means? Okay, then why this particular materials characterization is going to be important. Okay, then if you decide that, okay, this is important for me, this particular type of characterization is important to me, what different type of equipments are going to be available to me? For example, if you want to study microstructure, for example, so you have optical microscope, you have scanning electron microscope, you have transmission electron microscope, you have atomic probe microscope, you have AFM, you have FIM. So there are so many equipments which are available. So what is going to give me what I exactly want? Okay, so that I have to decide. And for that, whether, and another question which usually comes to the mind is basically whether I should know the principles of the instrument. Do I have to know it really? Okay, so basically it is very important to know the principle of the instrument, because then you can analyze your results better. So if you do blindly a characterization, then it's not going to work. You most of the time you need to know the principle of the equipment, how it operates, and how to get good results out of it. For all those things, you will be required to know the principles of the instrument, how it works. Okay, and then whether there are some practical examples, like whatever material I am trying to characterize, are there any practical applications of it, or any other material has been characterized in a similar way, whether I can refer that. So I can give you some practical examples of this material characterization and what is a future trend in this area. Okay, so these are the questions which you usually try to answer whenever we say materials characterization. And in this particular course, I will be restricting myself to what you can say is the microstructural characterization of materials, because I think all of you are, most of you are mechanical engineers. So if you are a mechanical engineer, then I suppose that you know mechanical characterization very well. Like for example, tension test, compression test. So all this hardness, all these things are known to you. So I will be covering what is not known to you possibly. Okay. Now, what do you mean by characterization? So basically, when I say characterization, so there are three things which are involved. So one is the character, then the second one is the characterize, and the third one is the characterization. So character, basically, whenever we are trying to do characterization of a material, what we are trying to do is that we are trying to find a character of that particular material which is distinctive from the others. It's a special character of that particular material. So all those qualities that make a thing different from the others. For example, if you take all the metals, they are typically good conductors of heat and electricity. So we classify them as metals. We classify them as insulators. So whatever is not a good conductor of heat and electricity, we say it is an insulator. So like that, you have to find the character of the material which will distinguish it from all the other materials. Like another example would be like if you take steel, the microstructure of the steel is different from aluminum. The phases in steel are different from aluminum and composites and other materials. Okay, so that is what is I'm trying to find by using a characterization technique. Character of the material which is going to make it different from others. Then now once this character comes, so once again there are two types of things, qualitative and quantitative. So what is my interest? Like whether I want to do this particular thing qualitatively or I want to do it quantitatively, right? So whenever I want to associate a number with it, then I will have to go for quantitative characterization. Whenever it is sufficient for me that the particular thing is present or absent in that particular material, then it is sufficient for me. I will say it is a qualitative characterization. And when I say characterization, these are all the activities which are involved in finding the character of this material and quantifying it, either qualitatively or quantitatively. Okay, so that is what is my characterization. So some examples are given, some microstructures are shown. So here you can see that these particles are dispersed in a matrix. Here it is a thread-like structure. Here you are having fibers. So you have to find some character of the material which will distinguish it from the others. Okay, now this is what we call in materials engineering a materials tetrahedron. Okay, so you can see that in this particular thing, you have one synthesis and processing. You have particular composition of a steel. So in this particular case, an example of steel is taken. So you have a particular composition of the steel. You will be processing it, synthesis and processing of the material. Now this is going to change the microstructure of the material. Okay, so you have composition on one end, you have microstructure on the second end, and you have synthesis and processing on the third end. And all these three together, they are going to give you the performance or the cost of that particular material. Okay, now just as an example, if you take any steel, okay, so you can subject it to different type of processing. Like you can use it in the hot rolled condition, you can use it in the cold rolled annealed condition, you can use in the normalized condition, you can quench it. If carbon percentage is higher, you can quench it and you can temper it and you can use in that condition. Now in all these things, the composition of my steel is same. Just by changing the synthesis and processing conditions, I am changing the microstructure, which is in turn changing the properties which are affecting my performance. So basically, I have to optimize all of these things in order to get a desired performance. Okay. So now in this particular case, what we will be dealing with is the microstructure. Okay. So you can have mechanical characterization, you can have microstructural characterization. There is always a link between microstructural characterization and the mechanical characterization. If your microstructure is proper, your mechanical characterization will be proper. It is going to give you good properties, and ultimately it is going to affect the performance. And I want all these things at the lowest possible cost. So if I am a consumer, I want it at the lowest possible cost. Now, if it is a strategic application, I am not bothered about the cost. For example, if it is a defense application, I am not bothered about the cost. I only want the performance. So depending upon my need, I will have this materials tetrahedron. Okay. Okay, it's the same example. So this is just an example of, you can say, automobile industry. Okay, now whenever we say characterization, there are typically different levels of characterizations. There are different type of characterizations. So you can have, in general, they are classified as 5 different levels of characterization or material properties. So you can have macroscopic level. So you can have macroscopic level of the properties. So whenever I say macroscopic, that means I am only interested in, for example, from the design perspective. So in mechanical engineering, you have design of subject, machine design or materials design subject is there. So in that, what I am doing is that for that particular design, I want the strength of this particular material as this. I want bias this, I want UTS this, I want elastic modulus this. So I am concerned only with the macroscopic properties. I am not bothered what is inside. Okay, so I am not bothered what type of steel it is, what is the microstructure of the steel. I am just interested in the macroscopic properties. Okay, so that becomes my macroscopic characterization, or the first level of characterization. It is typically for mechanical and materials engineering. So both of them are involved in this macroscopic level of characterization. Then we go further deeper. Now I want to know like what this mechanical properties depend upon. Okay, so how these mechanical properties are dependent upon the type of steel or type of the material and the processing of the material. Then I will go to this level, microscopic level. So this is typically dealt with chemistry and material science and engineering. So this is what I will be talking about, microscopic level of characterization. Okay, then if I am still it is not sufficient, microscopic level is still not sufficient, then I will have to go to the molecular level. So which is typically dealt by chemistry people. Again, molecular is not sufficient, so I will go to atomic level, physics and chemistry, and then further it is not proper for me, then I will go to further deeper, physics, that is subatomic level. So depending upon what type I want, I will have different type of characterization techniques. Okay, so if you are interested in macroscopic level, you will be having mechanical characterization. If you are interested in microscopic level, you will be having structural characterization. Depending upon the properties, you can have thermal characterization. If it is an electrical material, electrical characterization, magnetic material, magnetic characterization, optical material, optical characterization. So depending upon what is my need, I will have to choose what exactly I want to do. So in this particular lecture, I have chosen this microscopic level. So I will be talking about microstructure of the material. Okay. So once again, the same thing. So some examples are given, like I have talked about qualitative analysis and I have talked about quantitative analysis. What do you mean by qualitative and what do you mean by quantitative? So I said that qualitative means basically just the identification of the phase present or the morphology present or the chemical constituent presence is sufficient for my analysis. Then I will be calling it as qualitative characterization. Okay. So if the presence of a particular phase or the absence of a particular phase is more than sufficient for me, I will be only going for qualitative characterization. Then if I want to associate a number with it, then I will be basically going for quantitative characterization. So these are some of the examples which are given. So I will give you another example, like for example, mining. Okay. So the first level of characterization which mining people do is qualitative. Like for example, if I am searching for gold, so I will have different locations where gold can be found. So the first level which I will be doing is qualitative. So I'll be seeing whether gold is present in that particular place or not. Okay, so that will give me the grading of that particular different places for this gold. Okay, where I should dig for gold. So this becomes my qualitative characterization. Now, once I have identified the potential sites where gold could be found, now I have to rate them, which is better and which is not better. Then what I will do, I will collect the samples from those locations. Then I will use some sort of a method in which I can associate a number with this particular gold. Okay, at this location, whatever gold is there, it will be this %. At this location, whatever gold is there, it will be this %. And accordingly, once again, I will narrow down my, you can say, the digging criteria based on this qualitative analysis and the quantitative analysis. Now, for all these things, you will need different type of equipments, different type of things. Okay, so qualitative analysis, quantitative analysis, first you have to decide. Okay, now, many times you must have observed that we talk about whenever we have a material, whenever we have a metallic material or a ceramic material or a polymeric material, we typically talk about 3 or 4 things. We talk about macrostructure. Okay, we talk about mesostructure, we talk about microstructure, and we talk about nanostructures. Okay, so now whenever I talk about macrostructure, the objects which can be observed by unaided eye, so that is what is a macrostructure. Or at the most, you can use a magnifying glass. So sometimes you use a magnifying glass. So magnifying glass typically goes up to, I think, 20x or 10x. And whatever magnifying glasses are there, they can go up to 10x. So at the most, either with the naked eyes or with a magnifying glass, you will be observing the material or the structure. So we call it as a macro structure. Now, where it will be used, typically castings, small ingots, where you want to see how that has been solidified, your material has been solidified. So this is basically your macro structure. Okay, very crude level. Then mesostructure. Now, microstructure is something which I observe at a magnification of 1000x, 500 to 1000x. That is what I call as a microstructure. So objects that can be viewed by means of an optical microscope, that we will be calling it as a microstructure. Now, whatever is there in between this 10x to whatever we can observe by using a optical microscope, we will call it as a mesostructure. Objects are on the borderline of visibility. Now, if microstructure, whatever microstructure is there, then I can go to another level, which is a nanostructure. So typically, objects having size between 1 nanometer and 100 nanometer, we call them as nanostructure. So if I want to observe nanostructures, it is not going to be possible by your conventional SEM. It is not going to be possible by optical microscope. For that, you will be needing a specialized equipment, which I think Vijay must have talked in the earlier lecture. So field emission gun, scanning electron microscope, transmission electron microscope, 3D atom probe. So all these things will be used for the characterization of nanostructure. So if you have a nano material, then you will be using different type of characterization techniques. When you are having microstructure, you will be using different type of characterization technique. Macrostructure, different type of characterization techniques. So these are some examples once again. So macrostructure, typical magnification 1x to 10x, common techniques, visual inspection, X-ray radiography, ultrasonic inspections. All of this you must have seen in NDT, non-destructive testing or non-destructive evaluation of the materials. There is magnetic particle inspection, then ultrasonic testing, then X-ray radiography. So all these things will be giving you things like production defects, porosities, cracks, and inclusions, which are fairly large in size. So these things will be fairly large in size. Okay. So you are having a component which is a big ingot. In that you are looking for defects. You are looking for porosities, cracks. So this will be your macrostructure. Then mesostructure 100x, microstructure 100x to 10,000x. So for this you will be using optical microscope, scanning electron microscope, and in these two things you will be looking for grain size, particle size. If suppose you are working with a powdered material, it will be particle size. If you are working with metallic materials, it will be grain size. Phases, what are the different type of phases which are present, whether there is anisotropy of the phases, chemical composition, and other things. And if this is not sufficient, then you will be moving to a higher level, which is dislocation substructure, grain and phase boundaries, precipitation. Now this thing will be more important in semiconductor industry. For metallurgical things, mesostructure, in between mesostructure and microstructure is good enough. But this will be required for semiconductor industry. For example, if you are making silicon wafers, it is usually a silicon single crystal. Entire wafer is a silicon single crystal. So in that there is something called as defect density. So dislocations will be there. So whatever is the permitted dislocation density, 10 dislocations per mm square or 1000 dislocations per mm square. So in that particular case, you will be required to see the dislocations or the defects which are at a very, very fine level, because you are going to make devices out of this silicon wafer. For example, whatever mobiles you have, in that mobile screens, you will be using silicon wafers. All your devices, you will be using this silicon wafers. So there is a fixed specification for them. So in that cases, you will be using specialized equipment for doing all these things. But yes, you can do that by using the characterization techniques. Similarly, for nanostructured materials, you can use X-ray diffraction, you can use scanning tunneling microscopy. So this is nothing but your AFM, HRTM, and likewise. So you will have to select the characterization techniques accordingly. Right? So what we will be talking about is a microstructure. Now, typically, the microstructure of an engineering material is a result of its chemical composition and processing history. So if you have a particular type of chemical composition and you have a processing history, your microstructure will depend mostly on these two things. For example, if you take steel, steel is an alloy of iron and carbon. So you have composition, and depending upon processing, you will have different type of microstructure, different type of phases. On the other hand, if you go to aluminium, then you have changed the composition, you have changed the class of the material completely, and hence your microstructures or phases are going to be different. Similarly for superalloys. So depending upon the composition, you will have the microstructure, and depending upon processing history, you will have the, you can say, distribution of the phases, size of the phases, precipitation of the phases. Okay. And all these things will be determining its engineering performance. So in our cases, bulk materials, we are typically interested in microstructure. In semiconductor industries, we are typically once again interested in microstructure, but at a nano level. So we call it as a nanostructure. Okay. Now, one thing is common in all the characterization methods. Okay. In all the characterization methods, you have one thing in common. You are going to have a source. Okay. You are going to have a sample and you are going to have a detector. So this source is going to throw out some signal. Okay. So this signal could be light. It could be X-rays. It could be electrons. It could be neutrons, or it could be anything. Okay. So this probe or the source is going to give out certain signal. Okay, with a certain intensity. Now you are going to have a sample. This sample will interact with this signal and it will give out secondary signals. Okay, scattered radiation, secondary signals, and we will be collecting these signals with a particular type of detector. Okay, and then we will be interpreting this particular signal. So whatever signals are coming out, we are assuming that they are giving you more or less the faithful reconstruction of your object. Okay, that is how your characterization works. You have a source which will throw some radiation or some light or electrons or neutrons, some signal onto your specimen. This specimen will have interaction with this particular signal. So you will be having a matter and signal interaction, and it will give out secondary signals which will be detected by a detector, and you will get the final result. Okay. Now, in case of optical microscope, we are using white light. In case of scanning electron microscope, we are using electron gun. In case of transmission electron microscope, we are once again using electron gun. In case of X-ray diffraction, we are using X-rays, and likewise. So depending upon what technique I am using, this probe will differ and this detectors will differ. But one thing is common: whatever signal is coming from the probe, that will interact with my specimen. It will give out secondary signal, and I will be detecting that. Okay, now, so this is all about characterization, a brief introduction to characterization. Now, why this particular microstructure is important? Now, you will see that there are microstructure sensitive properties and there are microstructure insensitive properties. So there are certain properties which are microstructure sensitive. There are certain properties which are microstructure insensitive. Now, in microstructure sensitive properties, you have yield strength, fracture toughness, thermal conductivity, and properties like this. Okay, so if you reduce the grain size, if you change the microstructure, yield strength will change, fracture toughness will change, thermal conductivity will change. So these are microstructure sensitive properties. Now, in a similar manner, you have microstructure insensitive properties like elastic modulus. So if you take any type of steel, the elastic modulus varies less than 10%. So whether you take a low carbon steel, whether you take a medium carbon steel, or whether you take a high carbon steel, this elastic modulus will vary less than 10% with change in temperature or with the change in alloy chemistry, grain size, or mechanical working. So this becomes my microstructure insensitive property. So if I want a change in elastic modulus, then I will have to change the class of the material itself. So instead of steel, I will have to use something else like aluminium or titanium. So then I will have a change in the elastic modulus. But within the steel class, I will not have a change in the elastic modulus, or the change will be very less. Now, thermal expansion is once again a function of temperature or pressure than microstructure. Okay, but it can be anisotropic. So thermal expansion coefficient is dependent more on the class of the material than the microstructure of the material. Similarly, specific gravity, density, and likewise. So there are properties which are microstructure sensitive. There are properties which are microstructure insensitive. So these are the properties. Now you must be aware of this Hall-Page equation. Okay. So this Hall-Page equation relates your grain size with the yield strength. So this is basically your grain size. Okay. So now why Hall-Page equation is very important? Because it is the only method, reduction of the grain size is the only method which will give you an increase in the toughness and an increase in the strength simultaneously. Okay, if you use any other method, what will happen is that strength will increase, but toughness will decrease. So this grain size, reduction in the grain size is important, because when you reduce the grain size, you increase the strength and you increase the toughness as well. So these two properties are very important as far as steels, aluminium, titanium, all other things are concerned. Okay, so this is what is basically your microstructure. So I have taken few examples, like this is your optical microstructure. So whatever you see in an optical microscope, you will get a microstructure which is something like this. So I believe this is a 0.2 or 0.3% carbon steel. So all of you know that whenever we take a 0.2 or 0.3% carbon steel, you will have ferrite and you will have pearlite. So this dark patches, okay, this dark patches are pearlite, and this bright things, these are all ferrite grains. So you have proeutectoid ferrite and you have pearlite. Pearlite is basically nothing but composed of ferrite and cementite. So if this particular thing is more than sufficient for you, then you will go for optical microscope. You will say that my characterization is complete. Now, for example, many times it will happen that, okay, I want to go further deeper. I want to see how the pearlite is distributed and what is the interlamellar spacing of pearlite, how cementite and ferrite are distributed in this pearlite. Now, this you cannot do by optical microscopy because there are inherent limitations to this optical microscope. So you will move to the second level, that is scanning electron microscope. So first level, optical microscope, then second level, scanning electron microscope. It is a similar sample. You will see that now you can see individual lamellas of pearlite. So one is cementite and then ferrite, cementite, ferrite, and like this you can have the lamellas. You can measure the interlamellar spacing. You can see whether it is coarse or fine. So you will be moving to the second type of level, that is from optical you will be moving to SEM. Now you will feel that, okay, now this is also not sufficient for me. So let's say there are a few carbides in your sample. So you want to see how they are distributed. You want to find out the chemical composition now. You want to find out the chemical composition at the microstructural level. So then you will move to the third one, which is SEM EDAX. That means scanning electron microscope with a attachment to measure the chemical composition at individual points in my microstructure. So this is basically your tin oxide on tin. So these are tin globules and on which tin oxide is coated. So you can find out where tin oxide is and where tin is. Okay, now still this is not sufficient. Then I want to see how substructure is there, how defect structure is there. Then I will go to transmission electron microscope where I can see the defects, where I can see the nanograins, where I can see the nanoparticles. So SEM EDS will also have certain limitations. Okay. Then further, if TM is not sufficient, then I will go to HRTM. So here you can see that you can see the individual lattices. Okay. You can see the dislocations. You can see the twins. You can see whether your precipitates are coherent or incoherent. So coherent means they are whatever interface is there, that is gradually changing from the precipitate to the matrix. Okay. So for example, if you take superalloys, why do they have high temperature strength? Because they are having coherent precipitates. Coherent precipitates are difficult to be cut by dislocations, and hence you get high temperature strength. So depending upon what level you want, you will have to choose the equipment. Okay, now having said all these things, people will ask, what is microstructure? Okay, now what is microstructure? So this is taken from Thermomechanical Processing of Metallic Materials book, written by Professor Indradev Samajdar. So my microstructural features are typically, you have phase, you have grain. So in general, whenever I say microstructure, it is the size, shape, distribution and orientation of different phases present in my material. Okay, it is very important: size, shape, distribution and orientation. So we will not be talking about orientation, size, shape and distribution, right? So for example, if I am interested, let's say I am interested in tool steels. In tool steels, you have, it is basically a high carbon steel, and you are having a lot of alloying elements which are going to give you different type of carbides. Now, carbides, they are very small and they are uniformly distributed. Then it is going to give me very good hardness. It is going to give me very good wear resistance. Okay. So whatever properties I want from the tool steel. So that is what is my phase structure and the grain structure. Uniform composition, structure and properties. Phase structure can be altered through phase transformation. So then I will have to see basically how to alter them. It will be a part of your processing. But for that, I need to quantify it. I need to see it. I need to quantify it. I need to associate a number. What is good for my properties? What is bad for my properties? In a similar fashion, defect structure. So you have different type of defects. Like volume defects includes gas bubbles and cavities and inclusions. So this will typically form from the steel making stage or the casting stage. Okay. And then these others can form based on the processing. So you will have to characterize, and by using different type of microstructural characterization tools, you can characterize all these things. You can characterize the size, shape, distribution and orientation of the defects, of the phases, of the grains, of the localized chemical composition also. Now, since many people, I think you had 2 lectures related to additive manufacturing of metals. Now, in additive manufacturing of metals, segregation is one of the major problems, right? So you do not have a uniform chemical composition everywhere. So segregation, how to characterize this segregation of different elements at different location. So this you can do by using the microstructural characterization, by using a scanning electron microscope with a EDS, which I have shown in the last class, slide. Okay, so this is what is your microstructure. Now I want to characterize this microstructure. So there are typically different tools for characterizing this microstructure. So you have an optical microscope. So optical microscope is the cheapest. Okay, and you will find this in most industries. Okay, Then the next level is scanning electron microscope, and the third level is scanning electron microscope with the EDS. So this you will find in most of the industries. Okay, so let's see the optical microscopy first. So I have very briefly put the principle. Now, what is an optical microscope? Optical microscope is something which will give you microstructure at up to 1000x. So you can magnify your object 1000 times. Okay. Now here one comparison is made between different things, like resolution of my naked eye is 0.1 mm or sometimes 0.2 mm people write. So I can by visual eyes I can distinguish between two objects which are greater than 0.1 mm apart. So if they are closer than 0.1 mm apart, my eyes fail to distinguish them as two different materials. It will be one material only. Now, if you take an optical microscope and you zoom the same thing 1000 times, you can go up to 250 nanometers or 0.2 microns, 0.25 microns. So this is the limit of my optical microscopy. So in an optical microscope, I can distinguish between 2 points which are greater than 0.25 micron apart or greater than 250 nanometer apart. So if this is sufficient for me, it is okay. If not, then I will move to the next one. So what I'm doing, I am improving the resolution when I'm moving from this to this. Okay. Then if optical microscopy is not sufficient for me, then I will move to the third level. So you can see that there is one order of magnitude improvement in the resolution when I move from eyes to optical microscope. When I move from optical microscope to scanning electron microscope, I will have another improvement in basically resolution. So now I can distinguish between two things which are 2.5 nanometers apart, greater than 2.5 nanometers apart. So you can see here it is 250 nanometer, here it is 2.5, 100 times improvement. Now, once again, this is not sufficient, then I will move further, 0.5 nanometer. So accordingly, I will have to select my technique, what is sufficient for my, basically you can say process or the sample or the metal, whatever I want to characterize. Okay. Now, so first we will discuss, this is the only slide for the principle of operation of optical microscopy. All of you must have already seen it n number of times. Now in this, you can see this is my optical microscope. Here I will be having a source, or here I will be having a source, depending upon whether it is a reflected light optical microscope or it is a transmitted light microscopes. So now for metals and alloys, we typically use a reflected light microscope. For all the biological samples, we use a transmitted light microscope. So if you put your source here and sample here and detector here, then it becomes a transmitted light microscope. If you are having a source here, which is typically white light, so the light will come from this direction, it will hit upon your specimen, and once again it will go back to the detector. So this is my reflected light configuration. So depending upon whether I am working with biological samples or whether I am working with metallic samples, I will have a reflected light, transmitted light, or a reflected light microscope. And these are there are different parts of the microscope which you can use to optimize it. Now, whenever you put the sample here, the first image is formed by the objective lens. So you will see that this objective lens are the most important part of your entire microscope. Okay. So this objective, sometimes the cost of one objective is as high as that of the entire microscope, because this objective from the first image, the entire resolution what you are getting is by imaging from this objective. So if let's say I'm working with a metallic sample, so in the metallic sample, what I am doing, I am polishing this metallic samples. So I will be polishing this metallic sample and I will be etching this metallic sample. Now, if suppose you have a metallic sample, in that you will have different phases, you will have grain boundaries, you will have different type of phases. So what you do typically in a typical steel, you etch it with 2% nitrile, which is a mixture of HNO3 and ethanol. So what you do is that you take 100 ml of ethanol and you put 2 drops of HNO3 or 2 ml of HNO3 in that. So that makes it nitrile. Now you will be polishing this surface and then you will be passing a chemical over it. Now, once you pass the chemical over it, you will see that there are different grains which are there in the material. They all etch at a different rate. So whenever you pass a chemical over your material, what it does, whatever grains are there, they will be each at a different rate. And accordingly, you will get a different contrast for different grains. Now, this particular grain boundaries, this we call as a grain boundaries. This grain boundaries are higher energy areas. They will be etched much more than the rest of the matrix. So what will happen? Light is coming from this. When it is hitting the polished surface, it will go back. And when it is hitting this particular grain boundaries, it will go out. So that is why you will see that these boundaries, grain boundaries, are dark in nature because light is not going into the objective. Okay. And all these portions are bright in nature because light is getting reflected back. And that is how you create the contrast. So if you take just a polished sample, you will not be creating the contrast. You will have to pass a chemical over it. Okay. Once you pass the chemical over it, you will be having different phases, which will be etched at a different rate. You will be having different grains, which will be etched at a different rate, and you will be having different boundaries, which will be etched at a different rate. And accordingly, your sample is generating the contrast, and that is what we call the microstructure. Size, shape, distribution of grains and phases in my material. Okay, so this is how your optical microscope works. Now, okay, so these are some of the methods by which, if you are having a very small sample, you need to mount it. So this is a thermosetting resin in which you will be putting it, and then you will be polishing this surface, and you will be passing the electrochemical etching reagent over it. So there are different methods. So I will not discuss all those things, but I will just give you some examples of microstructure. So these are all coming from your optical microscope. Okay, so in optical microscope, actually it is a destructive technique, and resolution is typically 0.25 micron. So you will see that these are the solidification microstructures. So these are some of the solidification microstructures. So you can see that this is a lead ingot, and this is an aluminum ingot, small aluminum ingot. This is a big aluminum ingot. Now, all of you know that whenever you are having solidification in an ingot, you have a chill zone. So here you will be having fine grains, and then you will be having columnar grains, and at the center you will be having equiaxed grains. And along with this, it will be having directionality, how the heat is taken away from the ingot. So here you will see this shrinkage pipe. So you'll be cutting this ingot. So what we have done is basically, this is an example of macrostructure, not the microstructure. Okay, we have talked about macrostructure and the microstructure. So you will be taking this small ingot, cutting it into two parts, and you will be boiling it in a, I think the etchant is, you will be boiling it for 2 hours in dilute H2SO4. So then you will be seeing this grain structure. So this is an example of macrostructure. So whenever you are having ingots, you are having big grains, you will be going for macroscopic examination. Okay, so the casting solidified or crystallized from outside in. The casting is polycrystalline. The term polycrystalline means consisting of many grains, differently oriented grains or crystals. Right, so this was macrostructure. Then this one is an example of microstructure. Now, all of you must have studied heat treatment. Okay, so if you are taking a particular steel, you can get different type of microstructures just by processing it. Okay, so you take, let's say, a 0.8% carbon steel. So you can have a fully pearlitic structure. You can have a martensitic structure. You can have bainite structure, or you can have spheroidite, that means ferrite with cementite, globular cementite spheroidization structure. So just by changing the processing, you can have different type of microstructures, and then you will find that this different type of microstructures are having different properties. Hardness is different, tensile strength is different, ductility is different. Sometimes it is very brittle, sometimes it is very ductile, sometimes it is highly machinable. So all of these things are basically dependent upon your microstructure. So this first thing is an example of optical microscopy for a typically 0.8% carbon steel. So you will see that you can, now this is an optical microscope, but still you can see this pearlite and ferrite lamellas. So typically this is at 1000x. Now here you can see this pearlite lamellas because we have done furnace cooling, and the lamellar structure is very coarse. Now, once this lamellar structure becomes very fine, your optical microscopy won't be able to see it. So this is typically for a furnace cooled or an annealed material, and hence you are seeing very coarse lamellar structure. But yes, you can see the structure, how this structure is there. Now, typical examples for fully pearlitic steels are your rails. Okay, they can sustain very high compressive loads, and that is why typically you use 0.8% carbon steel in rails, right? So this is your effect of heat treatment on the microstructure. So this is your pearlite. Then similar steel, if you do a different processing, you can have a different type of microstructure. Now, this is martensite. You can see retained austenite, martensite. Now, this is typically martensite is very important as far as tool steels are concerned. So if you take all type of tool steels, typically they are having a martensitic structure. Whenever you require a very high wear resistance is generally correlated with your hardness. So you will you want to have a martensitic structure. Okay, so in those cases, in those steels, you will be seeing the microstructures which are needle-like, and you will be having retained austenite. Then you will be doing tempering. Okay, so after tempering, you will have ductility. Now here you will have some amount of ductility. Here you will have very negligible ductility because martensite is inherently very, very brittle. Okay, so you can quantify the martensite, you can quantify the retained austenite, you can see the microstructure. Then the next one is bainite. So just by changing the process, you can have a bainitic structure. Now this martensitic structure, you can convert it to this pearlitic structure, you can convert it to a spheroidized anneal structure by doing a very high temperature annealing, where all this pearlite, Fe3C and ferrite. So Fe3C will be converted into globules. Okay, now this type of steel will give you very good machining characteristics. This will give you very bad machining characteristics. Okay, so typically you add sulfur. So when you add sulfur, it promotes this spheroidization, and hence, so depending upon the microstructure, you can correlate, you can quantify it, you can and correlate it with your properties. So different types. So this is slow cooling from austenite region. That is what I call furnace cooling. Then quenching in water, isothermal transformation, spheroidization. So you can do different type of heat treatments, and you can get different type of microstructures. You can see them by using optical microscope, and by using image analysis, you can quantify them. Okay. Once again, a different structure. So now here, this is a cast structure. Okay. Now I have talked about segregation. So I was talking about segregation. So whenever you have a cast structure, so there is lot of segregation. Okay, lot of elemental segregation. So your microstructure, your entire microstructure is not uniform chemical composition. At some places you will have something rich, some elements will be rich, and at other places they will be lean. So your properties are not going to be uniform whenever you have a cast structure. So for that, what is done is that this is bronze. So you have copper plus 15% tin. So as cast, and then cast and annealed. Okay, so here you will have uniform structure. So you can observe the structures by using optical microscope, and this particular thing is an example of welding. So if you take a weld pool will have columnar structure, then you will have the interface, then you will have HAZ, coarse grain HAZ, fine grain HAZ, and then the base metal microstructure. So all these things are going to decide the properties. So whether post welding heat treatment is necessary or not necessary, whether that is related to the properties. So for all these things, you will have to do microstructural characterization, and your optical microscopy is the first level of your microstructural characterization tool. Now this is for an additively manufactured 316L alloy. So you can see that these are the solidification boundaries. So additive manufacturing, it is a layered technique. So layer by layer reconstruction of your object. So you can see that these are the different layers. Okay, so these are the melt pool boundaries. Now in this also a lot of segregation takes place, elemental segregation. So each layer is having a different chemical composition. So you will have to homogenize it. You have to check its properties. Okay, so all those you can do by using optical microscope and SEM-EDS. Right, so this is what is your optical microscopy. Now optical microscopy suffers from two limitations. One limitation is your, you can say, resolution. If something is smaller than 0.25 micron, even with the best possible optical microscope, you cannot see it. Okay. What type of, okay, so I will just answer it in few minutes. And now this is what is additively manufactured components. Okay. Now, depending upon your resolution requirement, depending upon your whether you want to do chemical composition, you will have to choose this technique. So optical microscopy will give you a overall structure of the material, but it will not tell you at what point what is the chemical composition. So the first thing is the first disadvantage of my optical microscope is resolution. If anything is less than 0.25 micron, I cannot study it by using optical microscope. Second, if I want to have localized chemical composition, for example, if you see different type of precipitates in this structure. Okay, so if you see different type of precipitates, you want to find out what type of precipitates they are. What is the chemical composition of those precipitates? You cannot do it by optical microscope. Okay, then the second one is it is a destructive technique. Okay, so you need a perfectly flat sample. You need a perfectly flat sample in order to observe it under optical microscope, because it is related to what is called as a depth of field. Depth of field of my optical microscope is very small. It is a destructive technique. So whenever you want to have localized chemical composition, whenever you want to have an improvement in the resolution, then you will go for other techniques. So the next level is basically your scanning electron microscopy. Now, before that, what type of characterization is preferable for 3D printed plastic polymer products? Now see, it will be dependent upon what exactly you want to look for. Right, plastics are actually low melting, so maybe you would like to look for a differential scanning calorimetry, TG, TC, TM. How much that particular polymer is crystalline, how much is amorphous. So for that you will have to use DSC. Microstructure will have a less role to play there. Maybe you would like to see the interface. So if you want to see the interface, then definitely you will go for something like SEM or an optical microscope. So it will depend upon your interest. What type of characterization is has to be done for polymer. So in general, polymers, we typically would like to do how much crystalline it is and how much amorphous it is. So whenever you do a 3D printed thing, how much crystalline portion is there, how much amorphous portion is there, and likewise. So it will, for polymer, it is going to be completely different. Okay. For additive manufacturing printing property, how can we choose best grade among stainless steel? See, it is not the best grade. It is usually the availability of the powders. Okay. So 316 is readily available in India. This powders, see, additively manufactured in additively manufacturing technique, you require basically powders. You require pre-alloyed powders. So whenever you are having pre-alloyed powders, so these powders are usually very costly. So if that powder is available, then you can use it, and you'll have to play with the processing parameters. For example, how much overlap should be there between the two simultaneous layers? How much should be the hatch rotation? What should be the speed of deposition? So all those parameters you will have to optimize, because in general, in additively manufactured components, you are going to have porosities. So if you take a cast component, they are 100% dense. Okay, if properly casted or properly manufactured. So they are 100% dense, but when you do this 3D printing of metals, you will have porosities. So sometimes it will be 99.9%, but whether that 0.1% is permissible or it is okay for you, that you have to decide. So you'll have to check for the mechanical properties. Okay, you'll have to check for the microstructure. If that porosities are very big, they can cause embrittlement. So all those things you will have to check. Right, Ritesh? Okay, so we'll move to the next one.
Rajesh.
Yes.
We can take at least 5-7 minutes break.
Yeah, we can take. Yeah, because
yes,
before starting the next technique, I think it is better to take a break.
Yes. So okay. We can take 5-7 minutes break. Okay, after that we can start. Okay, Dr. Rajesh, we can start. So, Dr. Rajesh, can we start?
Yeah, we can start.
Okay.
Okay, so first I'll answer these questions. See, it doesn't require for journal that you should have optical or SEM. Generally, what I see is features. What features should be there in the microstructure? Like whether optical gives me best or SEM gives me best or TM gives me best. So I have, you will not see any microstructures in journal papers which are optical. But if you see my papers, I put optical microscopes also. So wherever you get the necessary contrast, wherever you see the image which is nice, you see all the features, you should put that image. It may be optical, it may be SEM, or it may be TM, doesn't matter. So actually your interest should be what are the features you are looking for. Okay. And images are never colorful. Okay. So only optical microscope images are going to be colorful. Right. So optical microscopy, because see, for optical microscope, you are going to use white light. White light is having a wavelength range 700 to 1100 nanometers. So this is the range where you are going to get color. So for example, whenever you see color, these colors are basically how your eyes see the color, because all the colors fall onto a particular object. They are absorbed. Most of the colors are absorbed, and whatever reach your eyes, that you see as a color. So if red is reflected to your eyes, you will see it as red. If green is reflected to your eyes, you will see it as green. So in an optical microscope, I am using white light, which is having a wavelength range. You can say 400 to 700 nanometers, which is the wavelength range for color. And hence you can see colored images only in optical microscope, and that too in a polarized light optical microscope. Okay, not conventional bright field or dark field. You will be seeing these images in polarized light optical microscopy. So if you have a polarized light optical microscopy, you can get colored images. Now to find TG glass transition temperature, DSC is suitable or XRD is suitable. XRD will not give you glass transition temperature. It will give you fraction crystallized and fraction amorphous in your polymer. So DSC is the best suited technique for your glass transition temperature, crystallization temperature, and melting temperature. Okay, so see, modulated DSC and normal DSC are completely different. So modulated DSCs, you will see the phase transitions which you cannot see in a normal DSC. Okay, but DSC is typically used to get TG, TC, TM, and other application of your DSC is to identify the type of polymer which is there. So for example, if you are making a blend of nylon 6 and nylon 66, if you take a sample of the blend and you put it in your DSC, you will see two melting peaks. So it will really depend upon your material, what exactly you want to do. Then difference between SEM and FESEM, so that we are going to discuss very briefly. FEM, see, SEM images are not going to be colorful because in SEM we are going to use source as electron microscope, right? So to publish in journal, I have already answered that. Okay, so now we'll go ahead. So I hope that this clarifies some of your doubts. Okay, so we will move ahead now. We'll move to the next topic, which is your scanning electron microscope. Now, I have already told you that in case of an optical microscope, you have three limitations. It is a destructive technique. You have to polish the sample because the depth of field is less, resolution is less. Okay, and hence you are required to move to a scanning electron microscope. You cannot take localized chemical composition in optical microscope. So you can see that this is your optical microscopy image. So this is a spring, which is a three-dimensional. This is your powders. Okay, so whatever powders you are using for additive manufacturing, these are those powders or any other powder which you can synthesize by different methods. So you'll see that whenever you take optical microscopy image, one part is in focus and the other part is out of focus. Now, if you try to focus this part, this will become out of focus. So here, this part is in focus, this part is out of focus. Now, if you try to focus this part, this will become out of focus. So this is related to what is called as a depth of field. So since the depth of field of my optical microscope is small, I am unable to focus these 2 points simultaneously. Here also same thing. Now, in case of a scanning electron microscope, you can see that this entire spring can be focused. All the parts of my spring can be focused simultaneously, and I can get the image of the entire thing. It is like a 3D image. Okay, just like what we see by an optical, our eyes, that is how you can have this image. Same thing with the powder. So you can see this powder. So now the primary reason for this is that the depth of field of an optical microscope is very large. Now, when I say depth of field, the ability of my probe to focus between 2 points simultaneously. Suppose these 2 points are at a different height. So my probe can focus at this point as well as this point simultaneously. It can give me the image of this point as well as this point. So that is what is my depth of field. So in case of optical microscope, it is very small and hence I need a perfectly flat sample. In case of SEM, it is very large and hence I can have a directly fractured specimen, and if I put it in SEM, I can observe it. So this is the advantage: high resolution and high depth of field. So these are the two things which are there in SEM. In addition to, I can have localized chemical composition analysis. Okay. So this is your typical SEM. So you will see that this is a portion where your source will be there. This is the entire column. And somewhere here you will be putting the specimen, and these are your different type of detectors, 1, 2, and 3. And this is the image on which you will be displaying. This is a CRT on which you will be displaying it. So an instrument for observing and analyze the surface microstructure of a bulk sample using a finely focused beam of energetic electrons. So you are going to use an electron gun here. Now, this electron gun, whatever electron gun you are using here, that decides the type of scanning electron microscope. So you can have, somebody asked me, what is the difference between a conventional SEM and a FESEM? So the source is the primary difference between a FESEM and a conventional SEM. Both the places you are going to use tungsten, but here you are going to use it in a conventional SEM, you are going to use a tungsten filament. In case of a field emission gun, you are going to use a tungsten polycrystalline tungsten or a single crystalline tungsten with a very fine tip. So the tip of the tungsten will be few nanometers. Then it will generate this electron beam here. So this will be connected to an electronic circuit. It will generate the electron beam, and here you will have electromagnetic lenses. So you will be having 2 condenser lenses, just like we have lenses in optical microscope. Here also you are going to have lenses. So you will be having 2 condenser lens and 1 objective lens, and then this will focus all this beam, this entire beam of electron onto your specimen. So your electron beam will travel. So the diameter of this, you can say this electron beam at the crossover is around 50 micron in case of a conventional SEM. It is something around 10 nanometer in case of a FESEM. Further, brightness is very high. So this beam will travel and it will hit your specimen, and you will have specimen matter interaction. Okay. So you will have generation of various signals through this interaction. So these signals are typically secondary electrons, backscattered electrons, forescattered electrons, EDS, and WDS. So you can do basically signals will be only three: secondary electrons, backscattered electrons, and characteristic radiation. So this EDS and WDS are the methods of measuring those signals. Okay. Now, this secondary electrons are inelastically scattered electrons. Backscattered electrons are elastically scattered electrons. And your composition analysis is done by what is called as characteristic radiation. Okay, so this is the line diagram. So here you can see that it is in the form of a tungsten hairpin filament. Okay, so here you are going to have a filament. So this filament is in the form of a hairpin. Okay, so this is for a conventional SEM. So if you take a field emission gun, it will be in the form of a very fine tip. So this electron beam is generated here. It is traveling through the condenser lens, objective lens, and it is hitting your specimen. It is generating secondary electrons, it is generating backscattered electrons, and it is generating characteristic radiation, which are captured by a suitable type of detector, and that is what you will be analyzing. Okay, now, so this geometry is in transmission mode. So the same thing can be used for a transmission electron microscope. So you have a specimen. Now, in case of metals and alloys for SEM, typically we use a bulk specimen. What do you mean by bulk specimen? Bulk specimen means the specimen can be big. Okay, and it will be very thick. So if your sample is very thick, this part will not arise in SEM. So what will happen? Your electron beam will come in, it will interact with the specimen, it will generate secondary electrons. Now, what are these secondary electrons? These secondary electrons are inelastically scattered electrons. Okay. Now, when I say electron beam, what is an electron beam? Electron beam is nothing but a bundle of electrons traveling with a very high velocity. So what my source is generating? It is generating bundles of electrons which are traveling with a very high velocity. Now, let us say a few million electrons are present in my incident beam. They are traveling with a very high velocity. They are hitting my specimen. So let us assume that only one electron is there right now. So the first electron comes in, it interacts with my specimen. It loses its energy by multiple collision with the specimen and comes out as secondary electrons. So this becomes my inelastic interaction. Inelastic means there is a loss of energy. So initially my electron is traveling with a very high velocity. It is having a very high energy. After hitting the specimen, it loses its energy into the specimen and comes out as secondary electron. Okay, so this I call it as secondary electron, inelastically scattered electrons. Now, the energy range of secondary electrons is 0 to 50 electron volts. The energy of the incoming beam is 10 kilovolt, kilo electron volt, keV. The energy of this electrons is measured in keV. So the initial electron is having 10 keV energy, and the secondary electrons are having few EV energy. So there is a tremendous loss of energy, and hence we call it as inelastically scattered electrons. Okay, they come out from a surface of the specimen, surface layer of the specimen. Now the second type of radiation which we use is backscattered electrons. So my electron with a very high velocity comes in, it interacts with the nucleus and it gets rebounded back without much loss of energy. We call it as elastic scattering. So if the energy of my incoming beam is 10 keV, the energy of my backscattered electrons is also 10 keV. Secondary electrons, the energy of my incident radiation is 10 keV. The energy of my secondary electron is 50 keV, 0 to 50 keV. So there is a tremendous loss of energy. So inelastic scattering, elastic scattering. This characteristic radiation we will discuss later. So these two are used for imaging. Okay, these two are used for imaging in SEM. Okay, so I have not put that. Now you will see that the secondary electrons come out from a top few nanometer layer. Backscattered electrons come out from a top few 100 nanometers layer. And this characteristic radiation, they come out from a much larger depth. So that means if you measure the resolution, since secondary electrons are coming out from a very small layer, few nanometer layer, this will be having the highest resolution. Backscattered electrons, few 100 nanometers, they are having poor resolution as compared to secondary electrons, but better than characteristic radiation. Characteristic radiation are coming out from few micron depth. So they will be having worst resolution. Okay. So these are the three signals which we typically measure in SEM. Now, so you can see SC and reflected light micrograph of perlite in iron 0.1% carbon steel. So you can see the difference. So this image is basically your optical microscopy image. You can see that this perlite is not properly distinguished here. We cannot see anything. We just see it as a dark patch. Whereas if you go to SEM, you can see the individual layers. You can see whether this Fe3 is broken. Okay, so all these things you can analyze by using secondary electrons because it is having a much higher resolution. Okay, so this is an example of a resolution where resolution is important. Now let us say if I want to measure the chemical composition of this particular point, I can do it in SEM, but here I cannot do it. If I want to measure the chemical composition of these two different morphologies, so I can do it in SEM. I can put my electron beam here, I can capture the characteristic radiation and I can determine the chemical composition. I can do for here. So I can do for all the particles which are present in my microstructure. I can do all these things, which I am unable to do in optical microscope. So, but optical microscope will give me a rough idea what is there in my sample, then what to look for, and then I will move to SEM. So this one was 0.1% carbon steel. So that means it was hypoeutectoid steel. This is hypereutectoid steel. So that means greater than 0.8% carbon steel. So once again, on the right hand side, you have an optical microscopy image. So here you can see the cementite which is decorating the grain boundaries, since it is a hypereutectoid steel. And the same thing if you see in case of scanning electron microscopy, here you are unable to see the perlite colonies, lamellas. So but here you can see the perlite, you can see whether there is one colony or 2 or 3 different colonies. And this is how your cementite will look decorating the grain boundaries. So this is basically the difference in the resolution. So here you can see that this much length is representing 400 micron. Here this much length is representing 50 micron. You can further zoom and go up to a few lakh magnification also in case of a SEM, FESEM particularly. Right, so that is regarding resolution. So these two are the examples for resolution, and these are all secondary electron images. Okay, these are not the backscattered electron images. These are all the secondary electron images. Now, this is an example where your SEM is used for fractography. Right, now you have done a tensile test. Okay, in the tensile test, so this is an example of ductile fracture, typical cup and cone type of fracture. So this is your cone and this is your cup. Okay, so this is a ductile fracture and this is a brittle fracture. So typically whenever you have something like martensite, you will get a fracture like this. Whenever you have perlite or proeutectoid ferrite and perlite, you will get fracture which is like this. So it will be ductile in nature, it will be brittle in nature. Now many times you won't be getting 100% cup and cone fracture, but still you would like to find out what type of fracture it is. In those cases, what you have to do is that you have to see the microstructure under scanning electron microscope. Now here, this is for a ceramic material. Now all of you know that ceramic materials typically break in a perfectly brittle manner. All metals, typically ductile metals, they break in cup and cone type of fracture. So if you have a ceramic material and you would like to find out whether it is intergranular or intragranular fracture, you just have to see the fractured surface. Now, the advantage of SEM is that this thing you can directly cut from here and put it in SEM. This thing you can directly cut from here and put it in SEM without any sample preparation. Here also same thing, which is not possible in case of optical microscope. In case of optical microscope, if you want to see the microstructure, you will have to polish the sample. You have to make it perfectly flat so that it is within the depth of field of my optical microscope. So that is why you will see that whenever you want to do failure analysis, whenever you want to do fractography, you will typically go for scanning electron microscope. So all the industries nowadays, big industries like Tata Steel, JFW, they will all have SEM, Mukan Steel, Sunflag Steel, wherever you find that such type of requirement is there, you will have this thing. So these are the examples. So this is intergranular. That means your crack is propagating through the grain boundaries. This is intragranular. Crack is propagating through the grains, right? So the crack is propagating during fracture through the grains. Crack is propagating through the grain boundaries. So that means here your grain boundaries are weaker. So same thing can happen in metals. So if your grain boundaries are weaker, can we strengthen grain boundaries by doing some microstructural engineering? Okay, so that you need to find out. So once the crack starts here, it will propagate instantaneously and it will fail your material. Okay, and that is where once again your grain size will come into picture. I have told you that grain size is the only method by which you can have an increase in the toughness and at the same time increase in the strength. So if you are having an intragranular fracture, so if your grain size is small, this grain boundary will hinder the crack propagation, and that is how you will get increased toughness as well as the increased strength when you reduce the grain size. So SEM can be helpful in identification of the fracture mode. So a few another examples. Now this is a powdered material. Okay, so this is a ball milled material. So after ball milling, how the particle size is changing. After ball milling, how powder particle size is changing. So you can see the micron bar. This is 5 micron. So this much length represents 5 micron. So here the particles very big. So generally in order to create nanomaterials, you do ball milling. You go on milling the material. So then the particle size goes on decreasing depending upon your ductility of the material and brittleness of the material. You can have this flat things, or you can have perfectly rounded or brittle fractured material. So you can see that when I ball milled for 20 hours, I get a refinement in the particle size, right? So I can quantify this image in order to get the particle size by using some software like ImageJ, right? So this is an example where powdered material is seen in an SEM, scanning electron microscope. So depending upon your particle size, you will have the choice of either the field emission gun scanning electron microscope or a conventional scanning electron microscope. Okay. Now, so this is a second example. Now there is another example. So now this is a failed sample. So you can see that these are the beach marks. Now this is a fatigue. So fatigue test was done. So this on this circular sample, fatigue test was done. So you can see that there are multiple origins of fracture. And these are the beach marks. Beach marks means typically you have intermittent loading, change in the loading. So these are the places where it represents that there is a change in loading. And once this crack has propagated and the section size has become smaller, it has ultimately failed instantaneously. Until this, the crack was propagating. Now these are the beach marks which represents that load was changed at this particular locations. Now in this, so this is the image. Striations. So you can see that with each fatigue cycle, there is a creation of one striation. Okay, so this you are able to see because SEM is having a very large depth of field. Okay, and that is why you are able to see all these things. Now, and once again, non-destructively, you are preserving the entire surface and then seeing it without any sample preparation. Here also no sample preparation was done. The only requirement was there that your sample should be conducting in nature. So if it is non-conducting, you will just coat it with a thin layer of gold or some carbon, which is a conducting material. So fractographic analysis you can do, failure analysis you can do. So once again, you can see these things. So fatigue analysis, fatigue fracture analysis, powder analysis, failure analysis. So all these things makes your SEM a versatile instrument. Now I spoke about determination of chemical composition at the localized point. For example, if I am having an alloy, let's say, I am putting for ball milling, I am putting two materials, whether there is a formation of solid solution or whether this particle exists individually. For that, I have to do chemical composition of this particle. I have to do chemical composition of this particle. Okay. So for such analysis, we attach what is called as a EDS or a WDS to SEM. Now what it does, your electron beam is a high energy beam. It is having a very high energy, 10 keV. So I have a particular type of atom. So chemical composition is nothing but elemental composition. So I am having K, L, M, N shells. So my electron beam comes in, it knocks off a K shell electron, which is filled in by the L shell electron, and an energy equal to K alpha is given out. So suppose if I am having 100% iron, okay, what is the possibility of iron atoms? 100%. So everywhere I am going to have 100% iron atoms. Okay, now whenever I am having these iron atoms, so what will happen? K shell will consist of 2, 8, 8, 18, and the last will be depending upon what is the atomic number. You will have the valence shell. So K shell electron is knocked off, which is filled in by the L shell electron, and in the process an energy equal to K alpha is given out. Similarly, it can be filled in by the M shell electron, so K alpha, K beta, L shell electron knocked off, L alpha, L beta. So like that, if I am having 100% iron, K alpha, K beta, L alpha, L beta is given out of iron. Now somehow, if I can analyze this energy, I will be able to comment on the chemical composition. So that is what exactly we do in EDS. We either analyze the energy or we analyze the wavelength. Once we analyze the energy, it is called as energy dispersive spectrometer. Whenever we analyze wavelength, it is called as the wavelength dispersive spectrometer. Principle remains the same. Okay, so I will not go into these details. I will just show you some of the examples. Yeah, so secondary electron image and the backscattered electron image. Now let us say I am having a material in which there are two places. So I have deposited some high atomic number element here. Okay, and here I am having a low atomic number element or a matrix. So this is my matrix, this is my high atomic number element which is deposited onto my matrix. Now you will see that whenever you take a secondary electron image, it doesn't give me any information about the phase. Okay. However, if I take a backscattered electron image, now backscattered, what are the backscattered electrons? Backscattering happens because of nucleus. Now, if I am having a higher atomic number, that means the nucleus is going to be heavier. Okay. So if heavier nucleus is there, more number of electrons will be scattered in the backward direction. So the backscattering electron tendency will be more at this location because it is consisting of high atomic number element. Here I am having low atomic number element, so there is no backscattering. Backscattering is less. So accordingly, I will get a contrast. But in a backscattered electron, I am not going to get the chemical composition. I can only say that at this particular location, I am having a higher atomic number element, and at this particular location, I am having a lower atomic number element. I am unable to comment on the exact chemical composition. However, if you do energy dispersive spectroscopy or a wavelength dispersive spectroscopy, let us say you are looking for carbon. Okay, carbon is usually unreliable by EDS. So I will only focus on oxygen, silicon, and iron. So you can see that at this locations, oxygen is more. So my matrix is rich in oxygen. And this particular area is lean in oxygen. Silicon, there is no presence of silicon anywhere. Okay. Now, if I map for iron, then I will see that this location is basically nothing but iron. So iron is deposited onto my matrix. So I can do all this analysis. So this is the entire area is taken into analysis, or I can just locate my electron beam at this particular area and then I can take a spectrum. Now, as I said that if my material is 100% iron, I will get K alpha, K beta, L alpha, L beta of iron. If my material consists of iron and aluminum, let's say, so I will get K alpha, K beta, L alpha, L beta of iron. I will get K alpha, K beta, L alpha, L beta of aluminum. So there are other lines, but they are very weak. Okay. So accordingly, if I can analyze somehow these energies, I can comment on the chemical composition, and that is what precisely energy dispersive spectrum does. It analyzes the energy of the incoming photons. Okay. Now the binding and this K alpha, K beta, L alpha, L beta, they are all stored in the library. So you can comment on what is present in my sample at this particular locations. So that is what your EDS is. So EDS can be used to find out the localized chemical composition. Now, but once again, another example. So this was a fractured specimen. Okay. So the type of fracture is ductile, but here you can see the particles. So I have what I have done is basically I have taken an EDS spectrum of this. I have taken an EDS spectrum of this. So you can comment whether iron is more or chromium is more and what type of precipitate it is, or silicon is more. So if silicon is more, you can immediately comment that it may be SiO2. If iron is more, then you can say that it is FeO inclusion. So all those sort of analysis you can do if you can find out the localized chemical composition. So this is finding the spectrum at each of this location. This is mapping for iron in the entire microstructure. So both the things you can do by using EDS or a WDS. The only difference between EDS and WDS is in terms of resolution. So EDS is having very low resolution, WDS is having very high resolution. Okay. So this is what is my SEM, EDS and WDS. Now, moving ahead, there is one more technique which is called as X-ray diffraction. Now, in the disadvantage of EDS and WDS is that we can get the localized chemical composition, but we cannot get the phase. What do you mean by phase? For example, iron can be present in the form of iron oxide. It can be present in the form of iron sulfide. So whether this particular is iron sulfide or iron oxide, that we will not be able to see just by looking at this spectrum. For that, I will have to use another technique which is called as X-ray diffraction. So in X-ray diffraction, typically you get different type of peaks. So let's say if you are having an amorphous material, you will get a spectrum which is something like this. Now, what is this spectrum? This spectrum is coming from the Bragg's law. All of you know the Bragg's law, n lambda equal to 2d sine theta. So here I am putting an X-ray source. Here I am putting a detector, and here I am going to have my powdered sample. Okay, so my X-ray beam is coming in. It is hitting my specimen. It is doing constructive and destructive interference of the elastically scattered waves, and it is going to give me a signal according to the Bragg's law. Okay, so I will be moving my source from 0 degrees up to 90 degrees. In a similar fashion, I will be moving my detector from 0 degrees up to 90 degrees. So theta, theta. So theta, theta makes 2 theta. So that is what is this scale. Now you will see that I'm having two things in this particular graph. I am having a location and I am having intensity. So the location is dependent upon the Bragg's law. Intensity is dependent upon what is called as a structure factor. Intensity is proportional to structure factor and location is proportional to the Bragg's law. So if you have a material, let's say iron, I know the lattice parameter of iron and I know the crystal structure of iron. 1 by d square equal to h square plus k square plus l square by a cube. So from that I can find out d. So for one particular type of interplanar spacing, I can have 1 theta. Lambda is going to be constant. And accordingly, I will get a spectrum. So this spectrum is characterized by location. So this location will be given by the Bragg's law. That means Bravais lattice. So all of you know that crystal structure is composed of two things. One is Bravais lattice and the second one is the basis. So my Bragg's law is giving me information about the Bravais lattice, which is coming in the form of location. And my structure factor is going to give me information about the basis. So here you can see that sigma Fn is the atomic scattering factor, HKL is the type of plane, X, Y, Z are the fractional coordinates of the locations of the atom locations. I'll not go into those much details because it will require another 1 hour. So you will get a graph which is like this. Now, if it is an amorphous material, you will get just a hump. If it is a partially crystalline material, you will get peaks superimposed on this amorphous hump. And if it is a fully crystalline material, you will get number of peaks. Now, this is one example, okay, of aluminium. So if you have aluminium, you will get typically sharp peaks. So I think I will take the second example, which is a two-phase material. Yeah, this one. Right. So this particular thing consists of two phases. One is your tantalum and the second one is tantalum carbide. So you will see that out of this, some of the peaks are of tantalum and some of the peaks are of tantalum carbide. Now, for X-ray diffraction, there is a body which is known as International Center for Diffraction Data. Now, what is its job? Its job is to take the pure material and store its diffraction pattern. So if you obtain a diffraction pattern from the unknown material, you can obtain all the peaks. And once you obtain all these peaks, you can compare it with the library to get what type of phases are present in your material. For example, if you take iron ore can be composed of Fe2O3, it can be composed of Fe3O4, it can be composed of FeO, and in addition to this, there could be a lot of other materials which are typically called as gangue materials. Okay, so whether it is having a major proportion of Fe2O3 or it is having a major proportion of Fe3O4 or FeO, that we don't know just by doing the chemical composition. Because what chemical composition will do? It is going to give me the total amount of iron present in my sample. It will not tell me how much of this iron is in the form of Fe2O3, how much of the iron is in the form of Fe3O4, and how much of it is in the form of FeO. So that we can get by using X-ray diffraction, because we will get peaks corresponding to Fe2O3, we will get corresponding to peaks corresponding to Fe3O4. Now, basically, these are different phases. Since they are different phases, they will have different crystal structure, and XRD is having one-to-one correspondence with the crystal structure. Okay, so these are just the methods by which we have done this. But you will see that in this table, there are two entities. So some of the entities are for tantalum carbide and some of the entities are for tantalum. And here you have this PDF. So whatever storage format they have, they call it as PDF. So they will be having this tantalum carbide and tantalum card, and then you will be determining that what your unknown material is composed of by comparing it with the library. Okay, so that is what is here. X-ray diffraction. So I will not go into the quantitative phase analysis of powdered mixture because that will once again take time. So Pankaj, I think I'll stop here. So the time is also
yes,
over.
yes. I think
So if you have any
think
questions, you can ask.
we can have a couple of quick questions and then. Sir, there is one question related with
Yes,
styration
anyone?
in fatigue material.
I hope all of you are there.
Rajesh, can you listen to me?
Yeah, if there are any questions, then
Sir, there is one question in chat box. Can you hear me?
General questions on characterization are also okay.
Rajesh, can you hear me?
Diber sizes means what? Fibers. Okay, fibers. See, SEM will be FESEM will be a better technique. So if you are having a fiber sizes which are very, very small, they are running in nanometer. Typically, you use FESEM. Length and diameter, you will have to cut your section accordingly. Okay. See, you will have to cut two sections. One is you have to observe them perpendicular, and you have to observe them parallel. Then you can get an estimate of length and diameter, because in one section you won't be able to get the length and diameter both. In one you will be getting diameter and length will not be observed in that. So you will have to make another sample for the diameter. Okay.
Rajesh, can you hear me? Okay, Rajesh, can we? Hello.
पंकज
हाँ
वो खत्म कर दिया है
Okay.
ठीक है तब तक वो क्वेश्चन आंसर कर देता हूँ है ना ओके
Rajesh, then can we wind up? Rajesh, can we wind up? Participants, can you hear me?
Yes, sir. We could hear you.
Okay. So I thank Dr. Rajesh Khatrikar for giving us a very nice presentation on characterization of the material. I hope the participants got the idea about the metallic material characterization and some of the ideas related with polymer characterization for their research. I once again thank Dr. Rajesh Khatrikar. So tomorrow we will meet once again with a new session. Thank you.